Welcome, dear friend, to this quiet corner of shared wonder. Take a gentle breath and let it out slowly, allowing the subtle currents of the air around you to carry away any lingering thoughts of haste or worry. What time is it for you? Right now, is the sun painting the sky with soft hues of dawn, or perhaps the moon casts its silvery glow through your window, wherever you are, whatever moment you find yourself in? Know that this is a space for quiet contemplation, a sanctuary where the mind can wander freely, unburdened by the need for quick answers or urgent decisions. We are simply here, together, to explore the grand tapestries of existence, not to conquer them, but to simply touch their threads with gentle curiosity. This is not about learning in the traditional sense, nor is it a place for medical advice or therapeutic guidance. No, this is an invitation to simply be, to float gently on the currents of cosmic ideas, to let the vastness of the universe become a soothing lullaby for the soul. Imagine everything you've ever known, every atom, star, planet, and galaxy compressed into a single infinite decimally small point. Then in an instant, it all explodes outward. Time begins, space unfolds, and the universe is born. This is the story we've been told, the Big Bang as the ultimate beginning. But is this the whole story before the first second ticked by? Before energy cooled into matter, before even the laws of physics existed as we understand them? What was there, a quantum vacuum, a collapsing universe, a higher dimensional collision, or something we don't even have the words for yet? Let's dig into some of the most mind-bending ideas in modern cosmology and approach the limits of what science and maybe even thought itself can reach. Space. The final frontier. A realm of infinite possibilities and mysteries that have puzzled humanity for eons. From the vast voids that punctuate the cosmos to the very beginning of time itself. We embark now on a journey, a quiet, winding path. As we explore the enigmas of the universe and ponder its future, imagine, if you will, that we are merely tiny, gentle motes of dust, drifting through the grand cosmic dance, witnessing its evolution and gazing into the distant future. We will seek the boundaries of the cosmos, wondering softly if there truly is an edge to all we know, or if the whispers of infinity truly stretch on forever. Beyond our wildest dreams, in the vast expanse of the universe lies a deep mystery that quietly eludes our understanding. It is a mystery that stirs our imagination and gently challenges our very comprehension of existence itself. It is the persistent, whispered question of what lies beyond the universe. As we travel through the silent, star-dusted corridors of space, we are faced with the profound and humbling realization that our vision is inherently limited. We are, in a sense, imprisoned within the confines of our observable universe. What lies beyond these shimmering boundaries remains a profound mystery, a cosmic curtain that softly envelops the most sacred secrets of existence. The very concept of beyond becomes a philosophical problem here, doesn't it? How can we truly comprehend a realm that lies beyond the reach of our perception, beyond the subtle touch of our most powerful instruments? This is a challenge that gently pushes the boundaries of human thought, sparking our curiosity and quietly encouraging us to seek answers, even if those answers only deepen the mystery. We are like tiny, curious eyes peering through a keyhole, trying to grasp the immensity of the room beyond. Everything we see, everything that can reflect or direct light to us, from the most intimate corner of a quiet room to the most distant, ethereal galaxies that can only be seen through the colossal eyes of our largest telescopes. All of this, dear friend, is our observable universe. It is the sphere of light that has had enough time to reach us since the beginning of the universe. Currently, the radius of this magnificent, visible universe is estimated to be about 46.5 billion light-years. Yet, If you listen closely to the cosmic whispers, you might remember that the age of the universe, the very fabric of time since its fiery birth, is only 13.8 billion years. How can we gently explain this apparent discrepancy? How can something that is only 13.8 billion years old have a visible radius of 46.5 billion light years? Well, it all comes down to the gentle, persistent expansion of the universe. Imagine a balloon slowly being inflated if you drew two dots on its surface. As the balloon expands, the dots would move further and further apart, even though they aren't moving across the surface in the traditional sense. They are simply moving apart because the fabric of the balloon itself is stretching. Similarly, as a result of this cosmic expansion, the areas from which light was emitted long ago are continuously moving away from us. And so, the light that reaches us today has traveled from regions that are now, due to this ongoing expansion, at a much greater distance than the simple light travel time would suggest. These 46.5 billion light years mark the boundary of our observable universe. The furthest reach of light's gentle journey to us, even if the entire universe stretches on infinitely. Modern cosmology does not yet know what may lie beyond this observed boundary. These cosmological limits, or horizons, are dictated by the very nature of light itself. You might wonder, for instance, why we don't see the night sky completely filled with the blazing brilliance of stars. Why there are vast, dark voids between them. It is because of these limits set by light. For example, light has a certain maximum distance from which it can possibly reach observers on Earth. It is as if there were a vast spherical barrier, a shimmering bubble of perception, around us. Beyond this invisible barrier, there are billions upon billions of other distant stars and galaxies, quietly existing. Yet their light has not yet had the time to complete its arduous journey to our eyes. This spherical limit is often referred to as the particle horizon. And then, there is another subtle concept, the event horizon. While the particle horizon establishes the distance from which light that was launched in the past can reach us now, the event horizon is a more profound boundary. It is the distance from the present moment beyond which any signals emitted now would never reach an observer in the future. Imagine sending a message in a bottle across a vast ocean that is constantly expanding. If the ocean expands too quickly, your bottle might never reach the distant shore, no matter how long it travels. That is the gentle, silent barrier of the event horizon. However, beyond these two concepts of perception, lies yet another quiet limit, the Hubble horizon. If space objects are beyond this particular boundary, it becomes impossible for us to see them. Even after billions of years, they are constantly moving away from us at a speed that eventually outpaces the very light they emit. Because of this relentless, subtle movement, it seems to us that the universe is limited, finite, enclosed within this bubble of observable light. Although, in fact, it is just light itself that is limited in its journey. Gently revealing only what has had time to reach us, you are well aware, dear friend, that the light coming to us from those bright, shimmering cosmic objects doesn't travel at an infinite speed. It has a very specific, unchanging pace. For example, our own nurturing sun is located about 94 million miles from the Earth. In this case, light will only take about 8 minutes to travel from its fiery heart to our blue-green sphere. And the quiet, unassuming star Proxima Centauri, our nearest stellar neighbor beyond the Sun, is located about 4.2 light-years away from the Earth. This means that light from Proxima Centauri would take about 4.2 Earth-years to complete its journey to us. So, it turns out that when we gaze at the vast tapestry of the night sky, we can only see events that happened a certain amount of time ago. In the past, yes, we can truly say that we look back in time when we look up at the stars at night. The light reaching us now from a distant galaxy is a fossil of its past, a gentle whisper from eons ago. So, to update our knowledge about some extremely distant object, such as the HD1 galaxy, which is located an astonishing 13.4 billion light-years away. We would need to wait the same amount of time again. 13.4 billion years. Provided there are no obstacles like enigmatic black holes gently devouring the light in its path. In particular, if we could somehow examine this galaxy in exquisite detail, we would gain precious insights into how our own magnificent galaxy, the Milky Way, was formed in the early, turbulent stages of the universe. Therefore, the very detection of light, this delicate, fleeting messenger, is of paramount importance for studying the majestic evolution of the universe. And it is thanks to this very principle, this quiet ability to peer into the past through light, that we were able to gently develop the profound Big Bang theory, the consequences of the Big Bang. That colossal, fiery genesis could not but leave a trace. Such a trace was indeed found, almost by accident, by two curious researchers in the 20th century. Back when scientists were still deeply pondering theories of the origin of the universe. In the mid-1960s, two astronomers, Arno Penzias and Robert Wilson, picked up a strange, persistent signal with their incredibly sensitive radio telescopes. This signal seemed to be coming from everywhere, in every direction, and with the same unchanging intensity, like a soft, pervasive hum throughout the cosmos. After much careful consideration and ruling out all known terrestrial interference, it turned out to be a profound remnant, an ancient echo, of the very first light that appeared in the universe. This pervasive glow is what we now reverently call the cosmic microwave background radiation, or CMB. It is the universe's gentle, enduring lullaby. In the very early stages of the Big Bang, the universe was an unimaginably hot and dense crucible. The temperature was so extreme that stable atoms simply could not form. Electrons and protons, the fundamental building blocks of matter, could not combine to settle into orderly atomic structures. The radiation of photons, the tiny particles of light, were constantly scattered from free electrons or absorbed by them. And therefore, light, that precious messenger, could not travel far. The universe then was like a dense, impenetrable fog, opaque and shimmering with heat. It was a time before clarity, before light could truly roam free. However, after approximately 380,000 years following the Big Bang, everything began to cool down. The universe expanded enough, and the temperature dropped sufficiently for the first stable atoms to gently form, with electrons now bound to atomic nuclei. Photons were no longer constantly scattered. The cosmos, in a profound and pivotal moment, became transparent. And with this newfound clarity, light was finally able to spread freely over long, magnificent distances. It is this ancient light, its temperature now cooled to just a few degrees above absolute zero, around 454 degrees Fahrenheit, that we record as the subtle microwave radiation. It can be seen, with the right instruments, in any direction from the Earth. At a distance of about 13.8 billion light-years, it is precisely because of this profound distance, this measurement of the light's journey, that scientists gently assume that the age of the universe is the same number of years, although, as you already know, dear friend, this may be only the limit of our vision, the edge of our cosmic bubble. Nevertheless, the CMB itself cannot be seen by human eyes. Its intensity, that whisper of first light, is far too low for our ordinary perception. This is due to the relentless, gentle expansion of the universe, which we have just quietly discussed. This expansion causes the light waves, those ancient cosmic ripples, to stretch and lose energy over their immense journey. So, when they finally reach us, they are barely visible, having shifted into the microwave part of the electromagnetic spectrum, far beyond the reach of our human sight. Despite its incredibly low power, this faint, pervasive glow, the CMB, allows us to look through the very crack of the beginning of the universe as we know it. The whole magnificent image of the past, that fiery, dense moment and its subsequent cooling, is revealed to scientists through its subtle patterns. It is thanks to the CMB that we now confidently know about the Big Bang scenario and how our world gently developed from an unimaginable singularity to this very moment in time. Thus, the map of the sky, where you can see the tiny, beautiful temperature fluctuations of this relic radiation, is like a spotted pattern. Here, the blue areas are slightly below the average temperature, hinting at regions of slightly lower density in the early universe, and the orange areas are slightly above it, indicating regions of slightly higher density. These subtle spots allow scientists to gently study the very evolution of stars and galaxies. For these density changes, often called the seeds of structure formation, are what ultimately formed the hot and cold spots of the CMB. In addition, the largest spots, covering about 1 angular degree in the sky, have become one of the most compelling proofs of the flat model of the universe. This means that, on a grand scale, the geometry of our universe is much like a flat sheet. Rather than curved like a sphere or a saddle, smaller spots, in turn, have revealed a wealth of invaluable data on the precise composition and age of the cosmos itself. Thus, the diligent study of the temperature features of the CMB has become yet another quiet, powerful proof of the existence of dark matter and dark energy, those elusive, mysterious components that make up the vast majority of our universe. Back in 2003, a group of astronomers led by D.N. Spergel found that the amount of dark matter and dark energy far exceeds ordinary matter by several times. According to the latest precise measurements, the amount of dark matter is approximately 26.8%, and the amount of dark energy is a staggering 68.3%. Finally, the CMB also gently revealed to scientists the approximate rate of the universe's current expansion, approximately 42 miles per hour per megaparsec. Thus, the CMB provides modern science with a wide range of profound information about the early and present universe. And in particular, it quietly helps us to understand what the future holds for it, how its cosmic story might unfold. It turns out that both the CMB and the various space horizons quietly limit what we can truly see and perceive from our gentle perch on Earth. Now, let's take an even closer look at what these space horizons truly are and whether we can still gently look beyond them. Seeking out the hidden wonders, reconstructing a vanished epoch. What physics can and can't tell us about less than zero. When we talk about the beginning of the universe, we often imagine rolling back the cosmic clock, rewinding the galaxies, the stars, the atoms all the way down to the very first moment. This picture feels straightforward, like running a film in reverse. In physics, we even have equations that let us do something like that. General relativity, our best theory of gravity in spacetime, allows us to take the current expansion of the universe and calculate backwards. We can shrink the size of the universe, going further and further into the past, getting a clearer picture of what things might have looked like just moments after the Big Bang. But there's a point where this breaks down. A wall we keep hitting. That wall is known as a singularity. To understand what that means, we have to start with what general relativity actually does. It describes how matter and energy curve space and how that curvature affects the motion of objects. According to Einstein's equations, if we plug in the current state of the universe, how it's expanding, what it contains, and how matter is spread out, we can predict what the past looked like. This works surprisingly well. It lets us rewind the universe all the way back to when it was less than a second old. But as we push further back, past a trillionth of a second, past even smaller slices of time, the numbers stop making sense. We reach a point where density and temperature shoot up toward infinity. Space becomes infinitely curved. The equations give outputs that don't describe anything real, just mathematical chaos. That's the singularity. It's a point where our current theories fail. In the case of the Big Bang, the singularity sits at time or TT equals to 0. It's the barrier to knowing anything about earlier times. In simple terms, we can say that general relativity can't describe the universe at the exact beginning or before it, because the math breaks down. The theory needs space-time to be smooth and continuous. But when the density of matter becomes infinite, space-time stops being smooth. It tears apart in a way. This tells us something deep about the nature of our understanding. It means there's a limit to what we can know by using general relativity on its own. No matter how good our measurements get, no matter how powerful our telescopes become, we can't rewind the cosmic movie past that point. Not with this tool. Now, you might think, why not use quantum mechanics instead? After all, quantum physics is the other major pillar of modern science. It describes particles, energy, and the behavior of matter on the smallest scales. But quantum physics has its own limitations. Quantum field theory. The version of quantum mechanics that combines particles with fields is built on a fixed space-time background. It assumes space and time are already there, smooth and well-behaved. That works great in many situations, especially inside particle colliders or atoms. But it falls apart when space-time itself becomes wild and chaotic, like it does at the Big Bang. To really describe the beginning, you'd need a theory that combines both general relativity and quantum mechanics into one single framework, something that can handle extreme density and high energy, but also deal with the warping and breakdown of space and time. That's what people mean when they talk about quantum gravity, a theory that doesn't yet exist in a complete tested form. Until we have that, we're stuck. Our current tools let us get close to the singularity, but not through it. This puts a hard boundary on any talk about k less than 0, also known as the time before the Big Bang. In classical physics, time is a line, and we can trace it in both directions. But near the Big Bang, the classical picture of time no longer works. In practical terms, it means we can't say what, if anything, was happening before t equals to 0. Some models try to push the boundary by changing how we view the earliest moments. For example, some versions of cosmology start the clock not at ti equals to 0, but at t 10 ti 3 seconds. What's called the Planck time. This is the smallest meaningful unit of time in physics. Below this threshold, quantum effects and gravity are both so strong that we lose all predictive power. It's not just that we don't have the data, it's that the rules themselves might no longer apply. It's as if the entire concept of time stops being meaningful. From this angle, the past isn't hidden, it's undefined. The tools we use to define time and space don't work in that regime. When density and temperature go beyond certain limits, when energy levels become extreme enough, even the language of physics, mass, distance, time starts to fall apart. This isn't the only time singularities show up in physics. They also appear inside black holes, if a star collapses past a certain point. General relativity predicts a singularity forms at its center, an infinitely dense point surrounded by a boundary called the event horizon. Inside that region, time and space behave in ways we don't fully understand. And once again, general relativity fails at the singularity. This parallel hints at something deeper. The Big Bang singularity and the singularity inside a black hole may have something in common. They might be two examples of the same fundamental problem, our inability to describe extreme conditions with our current theories. Wherever we push physics to its limits, whether at the heart of a black hole or at the birth of the universe, we run into the same wall. What all this tells us is that while our equations can take us incredibly far, they cannot take us all the way. We can describe the expansion of space, the cooling of the early universe, the formation of particles and atoms, but only from a certain point onward. And that edge matters because it shapes the kinds of questions we can ask and the kinds of answers we can trust. If someone asks what happened a second before the Big Bang, the most honest answer we can give with our current physics is we don't know and maybe we can't know. This shows us how far we've come and where the next breakthroughs need to happen. For now, though, we can only approach the beginning from one side, like looking at the edge of a map and wondering what lies beyond, knowing we can't draw it until we invent a whole new kind of cartography. The end of time's arrow. How entropy behaves in reverse and eternal models. We remember the past, not the future. We grow older, not younger. Heat flows from hot objects to cold ones, but not the other way around. All these patterns follow what scientists call the arrow of time, a direction in which events unfold. At the heart of this idea is a law of physics that has never been broken, the second law of thermodynamics. It says that in any closed system, entropy, the amount of disorder, will tend to increase over time in most of physics. The basic equations work the same way, whether time moves forward or backward. If you watch a video of two billiard balls colliding and then reverse it, the backward motion still looks like something the laws of physics allow. But if you watch a glass fall off a table and shatter, reversing that scene, watching shards fly up and form a perfect glass, feels wrong. That's entropy. It tells us that certain processes have a preferred direction. This one-way flow of entropy gives time its sense of direction in our universe, as far back as we can trace. Entropy has been increasing. The early universe was hot and dense, but it was also surprisingly uniform, and that's actually a low entropy condition, even though it might not sound like it. As the universe expanded, matter clumped together into galaxies, stars, and planets. These structures added complexity and, in the long run, more disorder. Eventually, stars will burn out, black holes will evaporate, and the universe will become cold and dark. An end stage called heat death. That would be the maximum entropy state. But if entropy defines the direction of time, what happens if entropy starts decreasing? Could time itself reverse in certain models of the universe? Entropy might actually run in the opposite direction during different phases of cosmic evolution. And that opens up the possibility that the arrow of time as we know it could flip. Instead of imagining that everything started with a Big Bang and has been expanding ever since. We can ask what might happen if the universe were to stop expanding and begin shrinking in standard cosmology. This could happen if gravity eventually overcomes the outward push of expansion. Space would begin to contract, galaxies would draw closer together, and the universe would collapse into a big crunch. In some versions of this idea, as the universe contracts, the entropy might not just continue to rise. Instead, the trend could reverse as matter gets squeezed back into a smaller and smaller volume. Some physicists argue that entropy could begin to decrease. That would mean the direction of time, at least as measured by entropy, would also flip. To observers inside that contracting universe, it would feel like time is still moving forward, but from the outside, it might look like time has begun to run backward. This kind of thinking has led to proposals in which the universe has two symmetric halves, an expanding half with increasing entropy, the one we live in, and a contracting half where entropy increases in the other direction. The two were connected at the point of lowest entropy, which would be the Big Bang. This doesn't mean time literally reverses in the way we experience it, but it means the thermodynamic arrow of time, the one linked to entropy, does. In one such model developed by Sean Carroll and Jennifer Chen, the idea is that the universe can spontaneously generate patches of low entropy space from a timeless background. These patches then evolve in both time directions away from the low entropy state. Each side sees itself as having a forward arrow of time, and both consider the low entropy point as the beginning. From their own internal viewpoint, each half of the universe sees time flowing outward from the middle. Another place where this idea shows up is in cyclic cosmologies. In these models, the universe doesn't have a single beginning or end. Instead, it goes through an endless series of expansions and contractions. After each big crunch, there's a new Big Bang. The cycle repeats, possibly forever. In these models, the universe resets itself with each bounce. The challenge is figuring out how entropy behaves through those cycles. If entropy keeps increasing with every cycle, it would eventually reach a maximum and the cycles would stop being meaningful. But if entropy can somehow reset, maybe through quantum effects or exotic physics, then the arrow of time could also reset. Each new cycle could start fresh with low entropy and a new direction for time. A more recent and technical version of this idea comes from the conformal cyclic cosmology proposed by Roger Penrose. He suggests that the distant future of one universe can be mathematically stretched and reshaped to look like the very beginning of the next. The idea relies on the fact that as the universe becomes cold and empty, all matter decays and only massless particles like photons remain. In such a state, the concept of time becomes meaningless because there are no clocks or changes left to measure. Penrose claims that this timeless state can then connect to a new Big Bang where time begins. Again, this idea might sound strange, but it's rooted in real mathematics, and it shows just how much our understanding of time depends on the presence of entropy. Without entropy, there's no direction. Without direction, there's no time as we know it. All these models share one idea in common. The direction of time might not be a fixed universal property. It might emerge only under certain conditions. Specifically, when entropy can increase if those conditions change. So, might time. This is very different from the everyday way we think about time as something absolute, always ticking forward no matter what. But in the world of cosmology, time is tied to the structure of the universe. And if that structure flips, bends, or repeats, then the flow of time might do the same. Of course, these are still ideas. They aren't yet proven. Some models require certain assumptions, like how gravity behaves at very high energies, or whether space and time themselves can stretch and rebound in just the right way. But they show that entropy isn't a background detail. And so by studying its behavior in unusual situations, we may begin to see time as something more flexible, something that could, under the right conditions, fold back on itself or even run in reverse. Beyond light and matter, could the universe have emerged from pure geometry? There's a shift happening in how scientists think about the universe's origin. For a long time, theories have focused on energy and matter particles colliding, fields vibrating, temperatures climbing to extremes. But now some researchers are asking a different question. What if the universe didn't begin with matter at all? What if it didn't begin with particles or even energy? What if everything we know, space, time, light, and atoms, grew out of something more basic, something like geometry itself? It sounds strange at first. We think of geometry as something we study in math class: shapes, angles, lines. But in physics, geometry can be much more than that. And some physicists now believe that before there was light, before there were forces, before time itself ticked its first second, there was geometry. Not the smooth kind we see in general relativity, but a deeper quantum form of geometry. This idea comes from a branch of research known as loop quantum gravity, or LQG. It's one of the main efforts to build a theory of quantum gravity. The same goal that string theory is aiming for. But loop quantum gravity takes a very different path. Instead of trying to fit gravity into the same framework as particles and fields, LQG starts from scratch. It doesn't assume that space is a smooth background. It says space is made of tiny building blocks just like matter is in this view. Space isn't a continuous sheet. It's a web made of tiny loops. These loops are not made of anything material. They are pure geometry. They carry information about how space is shaped, how it bends, how it connects to itself. Imagine a fabric, but instead of threads made of cotton or wool, these threads are made of space itself. The loops can twist and weave, forming networks that give rise to the space around us. These networks are called spin networks. Spin networks don't live in space. They are space. Every point in this network holds information about area, volume, and connection to nearby points. And just like atoms can combine to form molecules, Spin networks can evolve and change, creating larger and more complex structures. Over time, this network can grow, as it does. It gives rise to the space we live in. But how does this relate to the Big Bang in LQG? The Big Bang is a transition point where one kind of geometric state changes into another. In ordinary cosmology, we say the universe began at a singularity, but in loop quantum gravity, the singularity doesn't exist. Instead, space can only shrink so far. There's a limit because the loops that make up space can't be compressed beyond a certain point. It's like trying to squeeze a sponge. It can only go so far before it pushes back. This leads to the idea of the bounce instead of starting from nothing. The universe may have gone through a phase of contraction until it reached a minimum volume. At that point, quantum effects of geometry took over, space rebounded, and a new phase of expansion began. That expansion is what we now call the Big Bang. But it wasn't the beginning. It was the result of a bounce that came before. This idea is explored more deeply in loop quantum cosmology, a version of LQG that focuses specifically on the entire universe. It takes the spin networks and applies them to a simple symmetric model of space. When scientists run the equations backward in time, they find that the universe doesn't hit a wall at T0. Instead, the geometry transitions smoothly through a bounce. Time continues, but the direction changes. Before the bounce, there was a contracting universe. After the bounce, we get the expanding universe we live in today. All of this happens without matter playing the central role. In fact, these models show that geometry alone can drive the bounce. The loops of space, the structure of spin networks, the rules that govern how they evolve. All of it can produce a universe that looks like ours. Even before you add particles or light, this paints a picture of the universe that is very different from the standard Big Bang idea. Instead of time starting at zero, we have time flowing through a transition in the structure of geometry. What's especially powerful about this idea is that it might be testable, even though these loops are incredibly small, far beyond anything we can observe directly. They may have left traces in the early universe. The cosmic microwave background, or CMB, for example, carries patterns of light from when the universe was just 380,000 years old. If the universe went through a bounce instead of a bang, that early light might contain clues, tiny deviations, subtle fingerprints of quantum geometry. Some researchers have created detailed simulations of how the early universe would behave in loop quantum cosmology. These models show that certain features, such as the distribution of temperature fluctuations in the microwave background, could reveal whether a bounce happened. Others are studying the formation of primordial gravitational waves, which might carry signatures from before the bounce. These are difficult signals to detect, but new telescopes and observatories may one day be able to find them. The idea that the universe could come from pure geometry challenges how we think about what's fundamental. In standard physics, particles are the smallest pieces of reality. Electrons, quarks, neutrinos, all the matter in the universe is made from them. But in LQG, particles might just be features of the spin network, like ripples in a pond. Particles could emerge from the underlying structure of space. Instead of asking, where did matter come from? We now ask, where did geometry come from? And some researchers believe geometry doesn't need a beginning in the usual sense. It could be that the network of loops and connections simply it evolves, it shifts, it transitions. But it doesn't necessarily have to start from nothing. That idea is hard to grasp. Our everyday experience is built on space and time. We live in 3 dimensions. We move forward through time, and we see the world is filled with stuff. But if the universe comes from pure geometry, then all of that is secondary. Space and time aren't the background. They're the result. This is where physics starts to overlap with philosophy. If geometry is the root of everything, then the universe might not be made of stuff at all. It might be made of relationships, how things relate to each other, how positions and angles and curves connect across the network. Matter in that view is just the expression of these relationships. Reality is not a thing, but a pattern. Inflation's blind spot. What happened before the universe inflated inflation is one of the most successful ideas in modern cosmology. It explains why the universe looks so smooth on large scales, why it appears flat, and why tiny quantum fluctuations grew into galaxies and clusters. It describes a short period of time right after the Big Bang, when the universe expanded faster than the speed of light exponentially, doubling in size again and again in a fraction of a second. But for all its successes, inflation leaves out one major detail. It doesn't explain what happened before it started. This missing piece is sometimes called the pre-inflationary epoch. It's a blank space in the standard model of cosmology. We know that inflation must have begun around 1036 seconds after the Big Bang. But what set the stage for this enormous expansion? What was the state of the universe before inflation kicked in? The theory of inflation usually starts with a field called the inflaton. This field is not made of particles in the usual sense. It's more like a field spread across space holding energy. When this field is high up on its potential energy curve, it causes space to stretch rapidly. Eventually, the field rolls down its curve, losing energy and heating up the universe, creating all the matter and radiation we see today. But for this to happen, the inflaton field must have already been in place, sitting in a very specific state. Inflation tells us what happens if we have an inflated field ready to go, but it doesn't tell us why that field was there in the first place. It doesn't say how it got into position, why it had the right properties, or what created the space it inflated. So between the breakdown of relativity and the beginning of inflation, there's a slice of time we don't understand. What might have filled that gap? One idea is that the inflaton field was not the first field to exist. Some researchers have proposed the existence of earlier fields, sometimes called pre-inflaton fields, that shaped the universe in its earliest moments. These fields could have triggered changes in space, setting up the conditions inflation needed. They may have pushed the inflaton field into the right place, creating the high energy state that allowed inflation to begin. These fields might have had unusual properties. Some could have been unstable, decaying quickly. Others might have created small pockets where the right conditions for inflation appeared. In this view, our universe is one of those pockets. Inflation happened here, but not everywhere. Some explore ideas where the early universe was in a quantum state, neither fully classical nor fully defined. In this view, the entire cosmos was described by a wave function. This wave function didn't describe things like temperature or distance, but probabilities and amplitudes. At some point, the wave function collapsed into a classical state and inflation began. This kind of picture is common in quantum cosmology, where space and time themselves are treated as quantum variables. There are also attempts to build models that stretch smoothly from quantum gravity to inflation. One approach is to embed inflation within loop quantum cosmology. In these models, the universe contracts before expanding, at its smallest size. Quantum geometry takes over and replaces the singularity with a bounce. After the bounce, the universe enters an expanding phase, and right after that, inflation begins. The inflaton field is still there, but its behavior is influenced by the quantum geometry of the bounce. In these scenarios, the pre-inflationary universe contains real structure, perhaps a contracting universe, perhaps a mix of fields, perhaps even echoes from a previous cosmic cycle. Some of this structure might survive the transition and leave signals behind. Detecting these signals is difficult, but not impossible. Experiments like the Planck satellite have already mapped the CMB in great detail. Some researchers believe that signs of pre-inflationary physics could be hiding in areas of the sky where the fluctuations are slightly weaker or less random than expected. If the inflaton didn't start in a completely uniform state, or if it had a brief interaction with other fields that might leave fingerprints in the spectrum of density fluctuations. These small irregularities could be studied in the distribution of galaxies or the polarization of the CMB light. The physics of the pre-inflationary era is happening at energy levels far beyond anything we can recreate in laboratories. That makes it difficult to test theories directly. We have to rely on indirect evidence and be careful not to overinterpret small anomalies. Still, the possibility remains that we could learn something about what came before inflation, not just from deep theory, but from actual observation. If we can figure out what prepared the inflaton field, we might learn what laws or conditions came before the visible cosmos. That could push us closer to answering some of the biggest questions. Why is there something rather than nothing? Why does space behave the way it does? Why does time move forward? Others remain cautious. They point out that inflation works well even without knowing what came before. It may be that the pre-inflationary phase is unknowable in principle, that any signals from that time were erased during the violent expansion. Or it may be that the idea of before inflation is misleading. That time itself didn't have meaning before a certain point. Bubbles in the void. Eternal inflation and the infinite cosmic fracture. As the theory of inflation has developed further, something strange appeared in the equations. In many versions of the model, inflation doesn't just happen once and end. It continues in some parts of space, branching off and creating new regions where inflation ends in slightly different ways. This leads to a much bigger picture, one where our universe is just one pocket in a vast and growing cosmic foam. This idea is called eternal inflation. It means that while inflation ended in our part of space and gave rise to galaxies and stars, it may still be going on elsewhere. In fact, it may never stop. In some areas, space continues to stretch faster than light. And within that ever-growing space, little bubbles can form where inflation comes to an end. Each bubble becomes its own universe with its own physical conditions and rules. Fluctuations in the inflaton field might help the field roll down its energy slope, bringing inflation to an end. But in some patches, the field can randomly jump up the slope again, which would keep inflation going longer than expected. The regions where it ends are surrounded by inflating space that is still growing. And in that growing space, more patches appear. Some regions inflate longer, others shorter. Some never stop inflating. As this process continues, the structure of the universe becomes fractal. The bubbles don't collide or mix because the space between them is still inflating. That fast expansion stretches everything apart, pushing the bubbles away from one another faster than any signal can travel. Inside each bubble, inflation ends and the familiar universe begins. But the details of each bubble can be different. The laws of physics might vary slightly or drastically. That's because the vacuum state of the inflaton field can fall into different configurations. In some bubbles, the constants of nature might be similar to ours. In others, they might be wildly different. The masses of particles, the strength of forces, even the number of dimensions. These could all change from one bubble to the next. This idea that the laws of physics might not be the same everywhere is unsettling. In traditional physics, we expect that laws are universal, but in the multiverse picture created by eternal inflation, the laws might only be local. What we call the laws of nature might just be the specific settings of our bubble. In other regions, reality might follow a different script. Some physicists see this as a strength. If the multiverse contains all possible versions of physical laws, then we no longer have to explain why our universe has the exact properties it does. It just happens to be one of the many possible bubbles where life can exist. If a bubble has conditions that allow galaxies, stars, planets, and chemistry, then observers like us might arise and ask questions. This line of reasoning is called the anthropic principle. It doesn't explain the laws of nature from first principles, but it does explain why we see laws that support life. Others are uneasy with this approach. It's hard to test the multiverse directly. We can't visit other bubbles or communicate across the inflating space that separates them. Even if other universes exist, we may never be able to prove it. That raises questions about whether the idea belongs in physics or philosophy. Still, the logic of eternal inflation is hard to avoid. once the inflaton field is allowed to fluctuate. The rest follows naturally from the math. There are a few possible ways we might detect signs of other bubbles. One is through bubble collisions. If two bubble universes formed close to each other in space, and if inflation ended in both at nearly the same time, they might have collided early in their histories. Such a collision might leave a circular scar or a region of unusual temperature patterns in the CMB. So far, no such clear signature has been found, but researchers continue to search. Another possibility comes from the overall structure of the universe. If space has a fractal nature due to eternal inflation, it might lead to subtle effects in the distribution of galaxies or the way large-scale structures form. These effects would be extremely hard to measure, and any signal would be buried in cosmic noise. Some theorists have tried to build detailed models of how eternal inflation works. These models use probability distributions to describe where and when new bubbles appear. They try to calculate how likely different types of universes are and whether certain kinds of physics are more common than others. But the infinite nature of the process makes it difficult to define meaningful probabilities. If the multiverse contains an infinite number of bubbles of every possible kind, how do you measure how likely one kind is compared to another? This is known as the measure problem, and it's one of the biggest open questions in multiverse theory. In some versions of string theory, the problem becomes even more complex. String theory doesn't predict one vacuum state, but many. The number is huge, possibly 10 out of 100 or more different vacua, each corresponding to a different way of curling up extra dimensions or setting the values of physical constants. This vast landscape of possibilities is called the string theory landscape. Eternal inflation acts as a mechanism to explore that landscape. Each bubble universe might settle into a different part of the landscape, resulting in different fundamental constants and effective laws of physics. This concept of an infinitely expanding, branching multiverse is a profound shift in how we view our place in the cosmos. It suggests that our universe, with its specific laws and conditions, is not unique or specially chosen, but rather one among countless possibilities. It opens up the mind to an almost unfathomable scale of existence, where reality is not a single, grand narrative, but an endless, quiet symphony of parallel stories, each unfolding in its own cosmic bubble. As we gently contemplate this idea, we might feel a sense of both liberation and insignificance, liberated from the pressure of seeking a single, ultimate explanation for everything, and yet wonderfully small within a tapestry so vast that it dwarfs even our grandest imaginings. The thought that there might be an infinite number of other yous in other bubbles, living out slightly different lives under slightly different physical laws, can be a strangely comforting notion, a reminder of the boundless potential of existence itself. And so, we quietly drift through this cosmic foam, knowing that the whispers of infinity stretch far beyond our observable horizon, carrying with them untold numbers of universes, each a testament to the inexhaustible creativity of the cosmos. It is a thought to cradle softly, allowing its vastness to quiet the hurried rhythms of our minds, gently inviting a deeper sense of peace and wonder. The end of time. A gentle journey to the universe's ultimate fate. Since the very beginning of our species, we've looked up into the sky and pondered the vastness of the universe. We've counted the stars, those twinkling diamonds scattered across the velvet blackness, charted the constellations, tracing imaginary lines between them, and dreamed of what lies beyond our tiny corner of heaven. We've asked the simplest, yet most profound questions. What is out there? Are we alone? And then, a deeper, perhaps more unsettling question gently arises. Did we ever dare to truly think about the end? No, not the end of our fleeting human existence, not the gentle fading of our individual breaths, but the end of time itself. What will the last days of the universe truly look like? What will we see, hear, and feel in those last, hushed moments? Will everything go out with a final echoing bang, a grand cosmic finale, or will something completely unforeseen happen? A quiet, subtle transformation beyond our current imagining throughout history. Humanity has thrived on exploring the unknown, on reaching for the edges of understanding, gently pushing the boundaries of our knowledge with every curious step. Today, we embark on perhaps the deepest journey of all, a journey not across the boundless expanse of space, but a journey through the very fabric of time itself, a gentle passage to its ultimate, distant end, like grains of sand in an hourglass. Each passing moment brings us a tiny step closer to the inevitable conclusion of the universe. But how and when will it happen? And what does it truly mean for us, mere mortal beings? Caught in this immense cosmic sweep, we will cross unimaginable scales of space and time, traveling billions, even trillions of years into the future. This is a journey not of physical distance, but of time, a deep dive into the cosmic clock, all for the gentle sake of exploring the ultimate fate of the cosmos. This is our quiet journey to the end of time. Here we are now. Dear friend, in the Anthropocene, the age of man, our time, our era. This is an era defined by the colossal, yet often subtle, influence of our species on this beautiful blue-green sphere we call home. We have shaped, manipulated, and forever altered the very fabric of the earth, sometimes with a heavy hand, sometimes with a gentle touch, all in the blink of a cosmic eye. Think of the Holocene, for instance, an 11,700-year era in which all human civilization, from its earliest sparks, was born. It has nurtured us from our earliest days, from humble hunter-gatherers, quietly following the seasons, to the complex, technologically advanced societies we inhabit today. The comfortable, stable climatic conditions of the Holocene allowed us to flourish, to invent, to build, to create. It gave birth to agriculture, to writing, to the very notion of civilization itself, providing a gentle cradle for human ingenuity. Nevertheless, as we rushed forward, driven by our inherent curiosity and relentless progress, the losses on our planet became increasingly evident, a quiet, undeniable whisper in the wind. Our relentless thirst for resources, our continuous expansion, caused profound changes that quietly mark the end of the Holocene. Climate patterns are shifting in ways unseen for millennia. Extreme weather events are becoming the norm. A more turbulent rhythm to the Earth's breath, and the incredible biodiversity that once thrived is now under serious threat. Species disappearing like fleeting dreams. The delicate equilibrium that has nourished us for thousands of years is teetering gently on the brink. Our collective actions have, without a doubt, left an indelible mark on the conditions of the Earth, silently ushering in a new geological epoch, the Anthropocene. In this current age, our planet is alive, teeming with activity and vibrant with life. The sun, our luminous star, continues to provide its steady, comforting warmth, fueling the intricate web of life on Earth. The moon, our silent companion, still orchestrates the gentle ebb and flow of tides. And far beyond our solar system, galaxies continue their majestic, slow dance across the cosmic stage. The universe, in its current state, is still a place of immense activity, driven by gravity, nuclear fusion in stars, and the ongoing expansion of space. Stars are born in fiery nebulae, planets coalesce from dust and gas, and the cycle of matter and energy continues its grand, ancient rhythm. But this vibrant activity, this cosmic dance, is not eternal. Like all things, it has a lifespan, a quiet trajectory towards a distant, inevitable conclusion, the future of the universe. Dear friend, is not a fixed, predetermined path, but rather a series of possibilities, each influenced by the delicate balance of fundamental forces and the mysterious nature of dark energy. Scientists, in their gentle quest for understanding, have proposed several scenarios for the universe's ultimate end, each painting a different, profound picture of the cosmos's final moments. These scenarios are not predictions set in stone, but rather the thoughtful contemplations. Based on our current understanding of physics and the observed behavior of the universe, they are whispers from the distant future, carried on the gentle currents of cosmic time. One of the most widely considered scenarios, and perhaps the most melancholic, is known as the Big Freeze or heat death. Imagine, if you will, a vast ancient fire slowly fading, its embers growing cold. In this scenario, the relentless, accelerating expansion of the universe, driven by dark energy, continues indefinitely. As space stretches, galaxies drift further and further apart, becoming isolated islands in a vast, dark, and increasingly empty cosmos. The light from distant galaxies will eventually be stretched so much by this expansion that it will become undetectable, fading into an ethereal whisper, like a memory that can no longer be grasped. Stars, the luminous hearts of galaxies, will eventually exhaust their nuclear fuel. Smaller stars, like our Sun, will swell into red giants, then gently shrink into white dwarfs, slowly cooling over trillions of years until they become cold. Dark remnants known as black dwarfs. Larger stars will explode as supernovae, leaving behind neutron stars or black holes. Even these stellar remnants will not last forever. Neutron stars will eventually cool, and black holes, through a process called Hawking radiation, will slowly evaporate over truly astronomical timescales, far longer than the current age of the universe. Imagine a tiny whisper of energy slowly emanating from the profound gravitational depths until even the black hole itself is gone. In this distant, quiet future, the universe will become incredibly dilute, cold, and dark. Matter will be spread so thin that interactions between particles will become exceedingly rare. The energy density will approach zero, and there will be no sources of heat or light. Entropy, the measure of disorder, will have reached its maximum possible state, a state of perfect, uniform coldness. There will be no more ordered structures, no more temperature differences, no more energy flow. The universe will have achieved a state of ultimate equilibrium, a vast, silent, and motionless expanse of cold particles, drifting endlessly apart. Life, as we know it, would be utterly impossible in such a state. The dance of carbon, so vibrant in our current moment, would have long since ceased, its atoms scattered into the vast, lonely void. This is the Big Freeze, a quiet, gradual fading into eternal darkness. Another scenario, less widely favored by current observations but still a fascinating possibility, is the Big Crunch. This is the opposite of the Big Freeze, a cosmic retraction rather than an endless expansion. Imagine the universe as a giant elastic band that was stretched outward. But now, the pull of gravity is slowly, gently, yet inexorably drawing it back in. In this scenario, the universe's expansion eventually slows down, halts, and then reverses. This would happen if the total amount of matter and energy in the universe, including dark matter and dark energy, were sufficient to overcome the outward push of expansion as the universe begins to contract. Galaxies would start to rush towards each other, speeding up as the cosmic fabric shrinks. The light from distant objects would be blue-shifted, meaning its wavelength would be compressed, making the universe appear increasingly hot and energetic. Eventually, all matter and energy would be squeezed back into an incredibly hot, dense state, perhaps even recollapsing into a singularity, similar to the one from which it supposedly began. This would be a mirror image of the Big Bang, a fiery, ultimate compression, bringing the cosmic story to a violent, final conclusion. In some cyclic models, this Big Crunch could then lead to another Big Bang, Restarting the cosmic cycle, an endless dance of birth, death, and rebirth. A third, more exotic possibility for the universe's end is the Big Rip. This scenario also relies on the nature of dark energy, but in a more extreme way. If dark energy were not constant, but instead its density increased over time, it could lead to a truly catastrophic end. Imagine the accelerated expansion of space becoming so powerful, so dominant, that it begins to tear apart every structure in the universe. First, galaxies would be ripped apart, then individual stars and planets. Eventually, the very atoms themselves would be torn asunder, their fundamental particles isolated and flung apart by the overwhelming force of dark energy. Even space-time itself could be shredded, leaving behind nothing but scattered elementary particles, infinitely far apart. In a completely fragmented reality, this would be an ultimate, violent unraveling, a cosmic shredding of everything we know. The fate of our universe, dear friend, is intimately tied to the precise nature of dark energy. Is its density truly constant, leading to the big freeze? Or might it evolve over time, leading to a big crunch or a big rip current? Observations, particularly those related to the accelerating expansion of the universe, tend to favor the big freeze scenario as the simplest explanation for what we observe. However, the universe holds many secrets, and our understanding of dark energy is still in its infancy. The ultimate end remains a profound question, a cosmic whisper of what is yet to come. As we ponder these vast, distant futures, it's easy to feel overwhelmed by the sheer scale of cosmic time. Our own lives, fleeting moments in the grand scheme, seem almost infinitesimally small. Yet, it is within these brief moments that we experience the wonder, the beauty, and the mystery of existence. The carbon atoms that form our bodies, the very building blocks of life, are participants in this grand cosmic drama. They were forged in the hearts of ancient stars, scattered across the cosmos, and eventually gathered here on Earth to form intricate, conscious beings. Their journey, spanning billions of years, is a testament to the universe's ability to create complexity from simplicity, life from stardust. And so, even as we contemplate the universe's eventual quiet fade or dramatic conclusion, there is a profound beauty in the present moment. In the cosmic dance that is unfolding right now, we are here, witnessing a vibrant, active universe, filled with light, energy, and life. The stars still twinkle, the galaxies still swirl, and the gentle breath of our planet continues its rhythmic dance. The future, however distant or uncertain, does not diminish the preciousness of this present. Living cosmos, let these vast ideas, these contemplations of the universe's ultimate end, not stir worry within you, but rather a deeper sense of peace. For in the grand cycle of cosmic events, even endings are but transitions, whether it's a slow, quiet fade into darkness, a fiery, dramatic collapse, or a violent, final shredding. These are simply chapters in an unending story, a grand narrative far beyond our comprehension. Your own existence, woven from the fabric of this universe, is a part of this story, a tiny, precious thread in the boundless tapestry of time. Allow the gentle currents of these cosmic thoughts to carry you, not into fear, but into a quiet, profound acceptance of the universe's vastness and its endless unfolding. Feel the subtle rhythm of expansion, the quiet whisper of distant stars, and the serene possibility of a future yet unwritten. In this acceptance, there is a deep, comforting peace, a sense of belonging to something immeasurably grand, the end of time. A gentle journey to the universe's ultimate fate. Tiep Theo. As we gently contemplate the universe's ultimate fate, we are drawn deeper into the mysteries of dark energy and dark matter, those elusive, silent forces that truly orchestrate the cosmic ballet. We've spoken of the Big Freeze, the Big Crunch, and the Big Rip, each a profound possibility for the universe's ultimate conclusion. Yet, these scenarios are but whispers, hypotheses based on our current, limited understanding. It is as if we are reading a grand cosmic novel, but only possess the first few chapters. With the ending still being softly penned by the universe itself, imagine, if you will, the universe as a vast, intricate clock, ticking away through immense stretches of time. What powers this clock, and what determines its final chime? Much of the answer, we believe, lies hidden within the enigmatic properties of dark energy. For decades, scientists observed the expansion of the universe, knowing it was a gentle outward push, but always assuming that gravity, that familiar force that keeps our feet on the ground and planets in orbit, would eventually slow it down. It was thought to be a race between the outward momentum of the Big Bang and the inward pull of gravity. But then, a stunning discovery in the late 1990s sent ripples of profound wonder through the scientific community. The universe's expansion was not slowing down. It was accelerating. It was as if the cosmic clock was not just ticking, but speeding up its rhythm. This acceleration pointed to the existence of something mysterious, something we could not directly see or touch, something that was actively pushing the universe apart. We called this mysterious force dark energy. It is perhaps the most profound enigma in modern cosmology, making up roughly 68% of the total energy density of the universe. What is it we don't truly know? Is it a property of empty space itself? An inherent pressure that forces the fabric of the cosmos to expand? Is it a new kind of energy fluid or field? Something entirely beyond our current understanding of particles and forces? Or is it a modification to Einstein's theory of gravity, a subtle tweak to the very rules that govern the dance of the cosmos? These are the questions that keep the minds of cosmologists gently whirring. Year after year, the nature of dark energy directly dictates the universe's ultimate destiny. If dark energy is a constant, unyielding force, forever pushing space apart, then the Big Freeze is our most likely path. The universe would expand forever, stretching all matter further and further apart, leading to that quiet, cold, dark end we spoke of. Imagine a vast, infinitely diluted gas, where particles are so far apart that they can never meet, never interact, never form anything complex. The energy that once fueled stars and vibrant life would be spread so thin that it would be effectively non-existent. This is a universe that simply fades away, a slow, gentle exhalation into oblivion. However, if dark energy is not constant, if it can change over time, other possibilities quietly emerge. If dark energy were to weaken over cosmic eons, allowing gravity to eventually reassert its dominance, then the universe might indeed succumb to a big crunch. The outward rush would falter, then reverse, and all the galaxies, stars, and planets would begin their long, accelerating journey back towards a single, infinitely dense point. It's a cosmic rewind, a reversal of the grand expansion, ending in a fiery, ultimate embrace. Some might find a strange comfort in this cyclical vision, a universe that is born, lives, dies, and is reborn, an endless cosmic dance of creation and destruction. The idea of a phoenix universe, always rising from its own ashes, is a powerful and ancient one, echoing through many philosophical traditions. Then there is the more dramatic, perhaps even terrifying, possibility of the Big Rip. This scenario arises if dark energy actually strengthens over time, becoming more potent as the universe expands. Imagine a balloon that is not just inflating, but whose surface is becoming increasingly brittle, tearing itself apart as it grows. In this terrifying vision, the accelerating expansion would become so overwhelmingly powerful that it would overcome all fundamental forces. First, it would tear apart galaxies, then individual stars and planets. Eventually, the very atoms themselves, the building blocks of everything we know and are, would be ripped asunder, their constituent particles flung infinitely far apart. Even the fabric of spacetime itself might be shredded, leaving behind nothing but a chaotic, fragmented void. This is not a slow fade, nor a fiery embrace, but a violent, ultimate unraveling. A cosmic scream that ends all. Current observations, gathered with meticulous care by sensitive telescopes and probes, seem to lean towards the simplest model of dark energy, the cosmological constant. This means that dark energy's density remains uniform throughout space and time, like an intrinsic property of the vacuum itself. If this holds true, then the Big Freeze remains the most probable fate for our universe. But remember, dear friend, our understanding is always evolving. New data, new theories, new insights could always emerge, gently shifting our perceptions and revealing entirely new possibilities for the universe's ultimate destiny. The universe is a master storyteller, and its final chapters are still being written, far beyond our current gaze. The profound beauty in contemplating these distant futures lies not in knowing the definitive answer, but in the very act of asking the questions. It is in allowing our minds to stretch beyond the familiar, to grasp at concepts of time and space that transcend our daily lives, to consider a universe that fades to an eternal cold, or collapses in a fiery crunch, or is torn apart atom by atom, is to confront the ultimate impermanence of all things, even the grandest cosmic structures. Yet, within this vastness, within this fleeting existence, there's a quiet dignity, a preciousness to the vibrant, active universe we inhabit right now. Our own existence, brief though it may be in cosmic terms, is a testament to the universe's intricate dance. The very atoms that form our bodies, the carbon, the oxygen, the hydrogen, were forged in the hearts of ancient stars that lived and died billions of years ago. We are literally stardust, walking and breathing, observing and questioning. Our consciousness, our ability to wonder about the cosmos, is a remarkable product of this universe, a fleeting moment of self-awareness within its grand, unfolding story. The universe has created us, given us the capacity to reflect upon its mysteries, and in doing so, we become a part of its ongoing narrative. So, let the idea of the universe's ultimate end not stir fear or anxiety within you. Instead, let it bring a gentle sense of perspective, a quiet acceptance of the grand cycle of existence. Feel the subtle hum of the cosmic expansion, carrying galaxies further and further apart. Imagine the slow, majestic dance of celestial bodies, each on its own trajectory, towards a future we can only guess at. In this profound contemplation, there is a deep, comforting peace, a quiet understanding that everything, even the universe itself, is part of an eternal, unfolding process. Allow these thoughts to gently settle in your mind, like motes of dust dancing in a sunbeam. There is no need for urgency, no need for definitive answers. Simply allow yourself to drift, to wonder, to be present in this moment of quiet cosmic contemplation. The vastness of the universe, its ancient past and its distant future, can become a soothing presence, a gentle lullaby that eases the mind and calms the spirit. Beyond light and matter, could the universe have emerged from pure geometry, Tieptheo? We continue our quiet journey, dear friend, into the most profound depths of existence, asking a question that gently turns our conventional understanding on its head. What if everything we perceive, all the vibrant tapestry of reality, the very space we inhabit, the time that flows relentlessly forward, even light itself and the atoms that compose our being, what if all of this did not spring from particles or energy, but from something far more fundamental, something akin to pure geometry? It is a thought that resonates with an ancient, almost mystical quality. Yet it is born from the most cutting edge of scientific inquiries. Our everyday understanding of geometry is rather simple. Isn't it we learn about lines, angles, circles, and squares in school? We see them in the shapes of our rooms, the paths we walk, the very objects we touch. But in the realm of advanced physics, geometry takes on a far more profound and dynamic meaning. It is not merely a static blueprint, but a living, breathing entity that can bend, stretch, and ripple, shaping the very forces of nature. For a long time, the dominant theories of the universe's origin focused on immense energies and incredibly dense states of matter particles colliding in fiery maelstroms. Fields vibrating with unfathomable power. Temperatures so extreme that all known laws of physics struggle to apply. But now, a new whisper emerges from the minds of visionary scientists, suggesting that before the first photon danced, before the very concept of force existed, before time itself took its first gentle breath, there was, perhaps, only geometry. Only not the smooth, elegant geometry of Einstein's general relativity, but a deeper, more granular, quantum form of geometry. This profound idea stems from a branch of research known as loop quantum gravity, or LQG. It is one of the most ambitious and promising efforts to construct a complete theory of quantum gravity. A grand unified framework that would reconcile the two giants of modern physics, Einstein's general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the bizarre and wonderful world of the very small. While other theories, like string theory, pursue a similar goal, LQG embarks on a fundamentally different path, one that reimagines the very fabric of space itself, instead of trying to force gravity into the existing mold of particles and fields. LQG courageously starts from scratch, questioning the very assumptions upon which our understanding of reality is built. It proposes that space is not the smooth, continuous backdrop we intuitively perceive. Imagine looking at a seemingly smooth fabric, but if you were to magnify it endlessly, you would eventually see it's made of individual threads, intricately woven together, in a similar vein. LQG suggests that space, at its most fundamental level, is not a seamless sheet, but rather a discrete granular structure, woven from unimaginably tiny, fundamental building blocks. These building blocks are not made of matter, nor are they energy in the conventional sense. They are, in their purest form, tiny loops of geometry. These loops are not in space. They are space. They are the fundamental pixels of reality, carrying within them the most basic information about how space is shaped, how it curves, how it connects to itself. Imagine these loops as the most primordial threads of existence, twisting and weaving together to form intricate spin networks. These spin networks are not objects in space, they constitute space. Every point within these networks holds essential information about area, volume, and its connections to neighboring points, forming a delicate and dynamic web, and just as simple atoms combine to form complex molecules. These spin networks can evolve, shifting and rearranging themselves, giving rise to the larger, more intricate structures that ultimately form the space we inhabit. Over vast stretches of cosmic time, this primordial network gently expands and densifies, eventually blossoming into the familiar, seemingly smooth expanse we experience. How, then, does this elegant concept relate to the grand cosmic event we call the Big Bang in the framework of LQG? The Big Bang is not a terrifying, infinitely dense singularity, a point where all our equations break down and understanding vanishes. Instead, it is reimagined as a transition point, a profound shift where one geometric state smoothly transforms into another, the classical singularity, where density and curvature become infinite, simply does not exist in loop quantum gravity. Why? because the very loops that compose space cannot be compressed beyond a certain fundamental limit. It's like trying to squeeze a sponge beyond its inherent elasticity. There's a point where it simply pushes back, resisting further compression. This fundamental limit leads to the groundbreaking idea of the Big Bounce, instead of an origin from nothingness. LQG proposes that our universe may have undergone a phase of profound contraction, a cosmic inhalation, until it reached this minimum possible volume. At that critical juncture, the quantum effects of geometry took over, exerting a repulsive force that prevented further collapse. Space then rebounded, launching into a new phase of rapid expansion. This expansion, dear friend, is what we now call the Big Bang. But in this profound new perspective, it was not the ultimate beginning, but rather the elegant result of a cosmic bounce that preceded it. This notion is explored in greater detail within loop quantum cosmology, a specialized branch of LQG that focuses on the dynamics of the entire universe. When scientists trace the equations backward in time within this framework, they discover that the universe does not hit a brick wall at Tibuswo. Instead, the geometry smoothly transitions through the bounce. Time itself does not cease to exist or begin. Rather, its direction appears to change. Before the bounce, there was a universe that was gently contracting, drawing inward. After the bounce, we witness the expanding universe we inhabit today, gracefully unfolding outwards. And what is truly remarkable about these models is that this entire process can be driven by geometry alone. The intrinsic properties of the space loops, the intricate dance of spin networks, and the fundamental rules governing their evolution are sufficient to produce a universe that mirrors our own. Even before we introduce the concepts of particles or light, this paints a picture of the cosmos that is profoundly different from the standard Big Bang narrative. Here, time does not have a hard beginning at zero, but rather flows seamlessly through a dynamic transition in the very structure of geometry. The power and allure of this idea lie not only in its elegant simplicity, but also in its potential testability. While these fundamental loops are almost inconceivably small, far beyond the reach of our most powerful direct observation, they might have left subtle, enduring traces in the early universe, whispers from a time before time. The cosmic microwave background, CMB, that ancient, pervasive glow of first light, carries patterns from when the universe was only 380,000 years old. If our universe truly experienced a bounce instead of a bang, this primordial light might contain minute deviations, gentle fingerprints of that quantum geometry. Scientists are actively creating detailed simulations of how the early universe would behave in a loop quantum cosmology scenario. These models suggest that certain features, such as the precise distribution of temperature fluctuations in the CMB, could reveal whether a bounce actually occurred. Other researchers are intently studying the formation of primordial gravitational waves, cosmic ripples in spacetime that might carry signatures from the era before the bounce. These signals are incredibly faint and challenging to detect, but the relentless advancement of new telescopes and observatories offers a quiet hope that one day, we might be able to uncover these profound clues. The idea that the universe could originate from pure geometry gently challenges our most fundamental assumptions about reality. In standard physics, we are taught that particles, electrons, quarks, neutrinos are the smallest, most irreducible pieces of reality. All the matter and energy in the universe are composed of them. But in LQG, this hierarchy is subtly inverted. Particles might not be fundamental building blocks themselves, but rather emergent features of the underlying spin network, like ripples on the surface of a pond, arising from the fundamental structure of space itself. This shifts our core question. Instead of asking, where did matter come from? We now ask, where did geometry come from? And here, some researchers offer an even more profound thought. Perhaps geometry, this intricate network of loops and connections, doesn't need a beginning in the conventional sense at all. It might simply be, it evolves, it shifts, it transitions, but it doesn't necessarily have to arise from nothing. This concept can be deeply challenging to grasp, for our entire daily experience is built upon the familiar bedrock of space and time. We exist in three spatial dimensions. We perceive ourselves moving inexorably forward through time, and we see the world as undeniably filled with stuff. But if the universe truly originates from pure geometry, then all of these familiar perceptions become secondary. Emergent properties, space and time are not the pre-existing background against which events unfold. They are the result of this more fundamental geometric reality. This is precisely where the frontiers of physics gracefully merge with the profound questions of philosophy. If geometry is indeed the root of everything, then perhaps the universe is not made of discrete things in the way we usually imagine. Perhaps, instead, it is made of relationships, how different points in the network relate to each other, how positions, angles, and curvatures connect across the intricate weave. Matter, in this profound view, would simply be the intricate expression of these fundamental relationships. Reality, then, is not a static object, but a dynamic, ever-evolving pattern. It is a thought that invites us to let go of rigid definitions and embrace a more fluid, interconnected understanding of existence, to quietly dwell on this idea, to allow it to gently unfold in your mind, can be incredibly soothing. It removes the burden of finding a definitive first cause in the traditional sense. Instead, it offers a vision of reality as a self-organizing, self-sustaining process, where the very fabric of existence generates itself through its own intrinsic geometric rules. Imagine the universe not as something that came into being, but as something that is, in a constant state of dynamic transformation. This profound shift in perspective can quiet the anxious search for a definitive beginning and, instead, foster a deep appreciation for the continuous, unfolding wonder of the cosmos. As you drift with these thoughts, let the intricate dance of pure geometry paint itself in your mind's eye. See the tiny loops weaving, forming networks, bending and stretching to create the vast, luminous expanse we call home. Feel the subtle energy of connections, the silent ballet of relationships that underlie all of reality. There is a deep, quiet peace in realizing that the universe might be an elegant, self-contained mathematical poem, infinitely complex yet profoundly harmonious. Inflation's blind spot. What happened before the universe? Inflated. Tiep Theo. We continue our quiet journey, dear friend, gently pulling back the cosmic veil to gaze upon the mysteries that precede even the most accepted theories of our universe's birth. We've spoken of the Big Bang, a fiery genesis, and the idea of a big bounce born from the intricate dance of pure geometry. Now, we turn our gentle attention to one of the most successful and widely accepted ideas in modern cosmology, cosmic inflation. It is a concept that has gracefully explained some of the most perplexing features of our universe. Yet, like all profound insights, it carries its own subtle unanswered questions, its own blind spot. Imagine, if you will, the early universe, not as the smooth, uniform expanse we observe today, but perhaps as a lumpy, irregular landscape, full of sudden hills and valleys. The theory of inflation suggests that in a fleeting, unimaginably tiny fraction of a second, right after the Big Bang, the universe underwent an extraordinary, exponential growth spurt. It expanded faster than the speed of light, not by breaking any fundamental laws, but because the very fabric of space itself was stretching at an astonishing rate. It was like blowing up a balloon, not just quickly, but with such incredible force that every part of its surface doubled in size, and then doubled again, and again, countless times, all within a blink of an eye. This rapid expansion smoothed out any initial lumps and bumps, flattened the overall geometry of the universe, and stretch tiny quantum fluctuations into the vast seeds that would eventually grow into the galaxies and clusters we see today. This idea has been remarkably successful in addressing several perplexing puzzles. Why is the universe so incredibly smooth and uniform on large scales? Without inflation, distant regions of the cosmos that are now causally disconnected would have been too far apart to ever have been in contact. Yet their temperatures in the cosmic microwave background are almost identical. Inflation provides a beautiful answer. These regions were in causal contact before inflation stretched them far apart, smoothing them out in the process. Why does the universe appear so flat, like a perfectly taut drumhead? Rather than curved like a sphere or a saddle, inflation naturally drives the universe towards this critical flatness. And why are there tiny quantum fluctuations in the CMB? Those subtle hot and cold spots that eventually grew into the grand structures of galaxies and galaxy clusters? Inflation amplifies these microscopic quantum jitters, stretching them to cosmic scales, providing the perfect seeds for structure formation, for all its elegant solutions and compelling evidence. However, inflation carries a profound, quiet mystery at its heart. It doesn't fully explain what happened before it started. This is the pre-inflationary epoch, a blank canvas in our cosmic understanding. We can trace the story of inflation back to an incredibly early moment. Around 10 Marcia were 36 seconds after the theoretical Big Bang singularity. But what set the stage for this immense, accelerated expansion? What was the state of the universe just before the inflaton field? The mysterious energy driving inflation kicked into gear. The theory of inflation generally posits the existence of a hypothetical field, the inflaton field. Imagine this not as a collection of individual particles, but as a vast, pervasive field spread throughout all of space, imbued with enormous potential energy. When this inflaton field is poised high on its energy curve, it creates a powerful, negative pressure that causes space to stretch exponentially. Eventually, like a ball rolling down a gentle hill, the field slowly rolls down its potential energy curve. As it does, it loses its potential energy, converting it into a burst of ordinary matter and radiation, effectively reheating the universe and giving birth to all the particles and light we see around us today. This transition marks the end of the inflationary period and the beginning of the hot, dense Big Bang era as we traditionally understand it. But here lies the quiet, persistent question for this grand cosmic drama to unfold. The inflaton field must have already been in place, nestled in a very specific, high-energy state, ready to begin its momentous role. Inflation elegantly describes what happens if we have such an inflaton field, perfectly positioned and brimming with energy, but it remains silent on the profound questions of why that field was there in the first place. What brought it into existence? How did it acquire precisely the right properties to trigger such an extraordinary expansion, and what kind of space, if any, existed before this field began its inflationary dance? So, between the moment where Einstein's general relativity breaks down at the singularity and the moment when inflation supposedly began, there is a fundamental slice of cosmic time that remains shrouded in mystery, an ethereal mist veiling the very dawn of our universe. What subtle forces, what hidden realities, might have filled that enigmatic gap? One intriguing idea suggests that the inflaton field was not the very first field to emerge on the cosmic stage. Perhaps there were even earlier, more primordial fields, sometimes referred to as pre-inflaton fields, whose subtle influences shaped the universe in its most nascent moments. These hypothetical fields could have been the silent architects, gently triggering changes in the very fabric of space, carefully preparing the intricate conditions that the inflaton field would later need. They might have, in a sense, nudged the inflaton field into its privileged high-energy state, creating the perfect cosmic spring for the grand expansion to uncoil. These early fields might have possessed extraordinary, almost fantastical properties, Some might have been inherently unstable, decaying rapidly after fulfilling their cosmic purpose. Others might have carried different, exotic forms of energy or interacted with space-time in ways entirely outside our current understanding, bending the rules in ways we are only beginning to imagine. In some interpretations of this idea, these early fields didn't directly cause the inflationary expansion themselves. Instead, their role was more subtle, more preparatory. They might have gently smoothed out any initial, large-scale irregularities in the universe's nascent geometry, or subtly steered the cosmos towards the incredibly flat shape we observe today, thereby setting the stage for inflation to complete the work. Other models, perhaps even more intriguing, suggest that the early universe did not begin in a smoothly prepared, simple state at all. Instead, it might have been a maelstrom of turbulence, a chaotic sea of random quantum fluctuations, over unimaginable eons, perhaps. These chaotic fluctuations might have, by sheer chance, created tiny, isolated pockets where the precise conditions for inflation to spontaneously appear were met. In this grand, cosmic lottery, our universe, with its perfect inflationary expansion, would simply be one of those fortunate pockets, a cosmic island where the conditions were just right for life to eventually emerge and ponder its origins. Inflation, in this view, happened here, in our specific cosmic bubble, but not necessarily everywhere across the vast, underlying quantum foam. Yet another avenue of thought explores the possibility that the very early universe existed in a purely quantum state, a realm where reality was neither fully classical nor definitively defined. In this profound view, the entire cosmos, in its nascent moments, was described by a vast, complex wave function. This wave function did not speak in terms of precise temperatures or distances, but rather in a language of probabilities and amplitudes, a shimmering tapestry of possibilities. At some pivotal, yet mysterious point, this cosmic wave function is theorized to have collapsed into a classical state. Much like a quantum particle's wave function collapses to a definite position when measured. It was this collapse that, in this view, could have triggered the onset of inflation, bringing definition and order to the universe's nascent chaos. This kind of picture is quite common in quantum cosmology, a field where space and time themselves are no longer mere backgrounds but are treated as dynamic, fluctuating quantum variables, dancing to the tune of probability. There are also active attempts to bridge the gap, to build seamless models that smoothly transition from the realm of quantum gravity to the inflationary epoch. One particularly elegant approach seeks to embed inflation within loop quantum cosmology, a theory we gently explored earlier. In these integrated models, the universe begins not with a bang, but with a bounce. It contracts to its absolute smallest, irreducible size, a point where quantum geometry takes over and replaces the classical singularity with a gentle rebound. After this profound bounce, the universe enters its initial expanding phase, and it is precisely after this bounce that the inflationary period is believed to begin. The inflaton field is still present in these scenarios, playing its crucial role, but its initial state and behavior are profoundly influenced by the quantum geometry of the preceding bounce. In these more integrated scenarios, the pre-inflationary universe is not an empty, unknowable void. On the contrary, it contains real, discernible structure. It might have been a universe that was contracting before the bounce, a cosmic inhale before the exhale. It might have been a complex mix of various fields, subtly interacting and preparing the stage. Or perhaps, most poetically, it might even contain echoes from a previous cosmic cycle, whispers from a past universe that contracted and then bounced into our current existence. The profound hope here is that some of this ancient structure, some of these subtle echoes, might survive the violent transition of the bounce and the subsequent inflationary expansion, leaving behind detectable signals in our current universe. Detecting these incredibly subtle signals, these faint cosmic fingerprints from an era veiled in mystery, is an immense scientific challenge. It's like trying to hear a whisper from across a roaring ocean. But it is not impossible. Experiments like the Planck satellite, for instance, have already meticulously mapped the CMB, that ancient glow of first light, with astonishing detail, far beyond anything we could have imagined just a few decades ago. Some researchers hold the quiet belief that signs of pre-inflationary physics could be subtly hiding in areas of the sky where the temperature fluctuations in the CMB are slightly weaker, or perhaps less random, than what the standard inflationary model perfectly predicts. If the inflaton field didn't begin in a state of absolute, perfect uniformity, or if it had a brief, fleeting interaction with other, previously existing fields during its early moments, these subtle interactions might have left faint, almost imperceptible fingerprints in the spectrum of density fluctuations in the early universe. These tiny irregularities, these cosmic whispers from the past, could potentially be studied through the large-scale distribution of galaxies across the cosmos or by meticulously analyzing the subtle polarization patterns of the CMB light. It is a long, patient search, demanding the utmost precision and the most sensitive instruments. The physics governing the pre-inflationary era, if it existed, would have unfolded at energy levels far, far beyond anything we can ever hope to recreate in our terrestrial laboratories. This inherent limitation makes it incredibly difficult to directly test these profound theories. We are forced to rely on indirect evidence, on the subtle clues woven into the fabric of the cosmos, and we must proceed with great caution, careful not to overinterpret every tiny anomaly or subtle deviation. Still, the tantalizing possibility remains that, through diligent observation and ingenious theoretical work, we might eventually learn something profound about what truly came before inflation, not just from the elegant equations of deep theory, but from actual, tangible observations, faint signals carried across billions of years of cosmic evolution. If we can indeed unlock the secrets of what prepared the inflaton field, if we can understand the conditions and laws that govern that enigmatic epoch, we might be pushed immeasurably closer to answering some of the biggest, most profound questions that humanity has ever dared to ask. Why is there something rather than nothing? Why does space behave with such specific properties? And why does time, that most mysterious of all dimensions, appear to flow relentlessly forward? These are questions that resonate deep within the human soul, questions that have stirred philosophers and thinkers for millennia. Unlocking the pre-inflationary secrets could offer us a profound new perspective, a glimpse into the ultimate wellspring of existence itself. However, some voices in the scientific community remain gently cautious, preferring to acknowledge the limitations of our current knowledge. They point out, quite reasonably, that the theory of inflation already works remarkably well in explaining the features of the observable universe. Even without a complete understanding of what preceded it, it may be, they suggest, that the pre-inflationary phase is inherently unknowable in principle, that any subtle signals from that infinitely compressed. Violent era were utterly erased during the overwhelming, exponential expansion of inflation. Or perhaps the very idea of before inflation is misleading in itself. It might be that time, as we understand it, did not have meaning, did not exist, until a certain critical point in the universe's evolution. In this view, asking what came before time is like asking what is north of the North Pole, a question that is conceptually meaningless within the framework we use. These are not easy questions, dear friend, and there are no definitive answers readily available. But the beauty lies in the exploration itself, in the quiet audacity of the human mind to even conceive of such questions. To ponder the pre-inflationary epoch is to confront the limits of our knowledge, to stand at the edge of the known and gaze into the vast, shimmering unknown. It is a testament to our insatiable curiosity, our gentle, persistent desire to unravel the deepest secrets of reality. So, let us rest for a moment with this quiet thought. With the image of a universe poised on the brink of an unimaginable expansion, its past perhaps filled with quantum whispers and geometric dances, or perhaps an elegant, unknowable void, whatever the truth may be. The very act of contemplating it draws us closer to the heart of the cosmos, and perhaps to a deeper understanding of ourselves within its boundless expanse, the cosmic web threads of existence and the dance of structures. Imagine, dear friend, that the universe is not just a collection of scattered stars and galaxies, but an immense, intricate tapestry, woven from unseen threads and shimmering with celestial structures. When we gaze up at the night sky, we see individual points of light, each a distant sun, perhaps cradling its own planetary system. Then, with a gentle shift of focus, we perceive the graceful spirals of galaxies, vast islands of billions of stars, swirling in cosmic dances. But what if we could zoom out even further, beyond the confines of individual galaxies, beyond even clusters of galaxies? What would we see then? We would witness the cosmic web, the largest known structure in the universe, a breathtaking arrangement of matter that spans billions of light years. It is the skeletal framework upon which the entire cosmos is built, a silent, majestic testament to the gentle gravitational dance that has unfolded since the very dawn of time. This cosmic web is not a solid, uniform entity. Instead, it resembles a vast, three-dimensional spiderweb, or perhaps a colossal, intricate neural network. It consists of three primary components: filaments, nodes, and voids. The filaments are long, thin strands of galaxies and dark matter, stretching for hundreds of millions of light years, like shimmering cosmic rivers. Where these filaments intersect, they create dense, luminous regions known as nodes, which are gigantic clusters of galaxies, some containing thousands of galactic behemoths, all gravitationally bound together. And then, there are the voids, immense, cavernous spaces, largely empty of galaxies and matter, like vast, silent bubbles in the cosmic foam. These voids are not entirely empty, but they contain far less matter than the filaments and nodes. Their emptiness a stark contrast to the brilliant structures that surround them. How did this magnificent, large-scale structure come to be? It is a story that begins in the very earliest moments of the universe, with the subtlest of whispers. Remember our discussion of the cosmic microwave background, or CMB, that ancient light, which permeates the entire cosmos, carries faint patterns of tiny temperature fluctuations. These tiny variations, those subtle hot and cold spots, represent minuscule differences in the density of matter in the very early universe. The slightly denser regions, the hot spots, had a ever so slightly stronger gravitational pull, like tiny magnets gently attracting nearby particles. Over billions of years, these almost imperceptible density enhancements slowly, patiently, gathered more and more matter through the relentless, gentle tug of gravity as more matter accumulated. The gravitational pull grew stronger, accelerating the process. This is known as gravitational instability, a powerful mechanism that transformed microscopic quantum fluctuations into the grand, macroscopic structures we observe today. Imagine casting a handful of dust into the air. The dust initially seems uniformly distributed, but over time, if there were even tiny, imperceptible clumps, those clumps would begin to attract more dust, growing larger and larger until distinct. Swirling patterns emerge. The universe, in a sense, is a much grander version of this dust experiment, unfolding over cosmic eons. The denser regions, the initial seeds, slowly evolved into the filaments and nodes of the cosmic web, drawing galaxies towards them like cosmic magnets. The less dense regions, those cold spots, were gradually emptied out, as matter was pulled away towards the denser areas, forming the vast, silent voids. This process was profoundly influenced by dark matter. We've touched upon this enigmatic substance before, recalling that it makes up about 26.8% of the universe's total mass energy, far outweighing the ordinary matter that makes up everything we can see. Unlike ordinary matter, dark matter does not interact with light. Making it truly invisible, it doesn't absorb, reflect, or emit any electromagnetic radiation, so we can't observe it directly with telescopes. However, we know it's there because of its gravitational effects. We see its invisible hand at work in the rotation curves of galaxies, in the gravitational lensing of distant objects, and, crucially, in the formation and distribution of the cosmic web. Dark matter plays an absolutely critical role in the formation of large-scale structures because, unlike ordinary matter, it doesn't interact with radiation. In the very early, hot universe, ordinary matter was tightly coupled with light, and the intense radiation pressure would have prevented it from clumping together effectively. Imagine trying to form a dense cloud of smoke in a hurricane. The wind would simply blow it apart. But dark matter, impervious to this radiation pressure, was free to begin clumping almost immediately after the Big Bang, quietly forming the gravitational scaffolding for the cosmic web. These invisible dark matter halos, vast spherical clumps of dark matter, acted as the gravitational wells that slowly, patiently pulled in ordinary matter, eventually leading to the formation of galaxies and galaxy clusters along the filaments and at the nodes of the web. Without dark matter, the cosmic web as we know it would likely not exist, or at least it would be far less pronounced and complex. Ordinary matter simply wouldn't have had enough time to form such vast structures on its own. The largest individual structures within the cosmic web are often called superclusters of galaxies. Our own Milky Way galaxy, along with its nearest neighbor Andromeda, is part of a smaller group called the local group. This local group, in turn, is gently drawn towards a much larger concentration of galaxies known as the Virgo supercluster. But even the Virgo supercluster is just a tiny speck in an even grander structure. Recent observations have revealed an immense, sprawling supercluster that contains our own. An astounding collection of galaxies stretching across 500 million light-years and containing the mass of 100 million billion suns. We call this gargantuan structure Laniakea, which beautifully translates to immeasurable heaven in Hawaiian. It is a profound reminder of our humble place within this unimaginably vast cosmic tapestry. The discovery and mapping of the cosmic web have revolutionized our understanding of how the universe evolved. It shows us that the universe is not randomly distributed, but possesses an intricate, beautiful architecture, shaped by the gentle, relentless hand of gravity over billions of years. It is a dynamic structure, still evolving today. Filaments are still pulling galaxies towards their nodes. Voids are slowly growing larger as the expansion of the universe stretches them, and new clusters are gently forming where streams of matter converge. As we ponder this vast, interconnected network, we might feel a sense of profound belonging. Every atom in our bodies, every star in the night sky, every galaxy in the distant cosmos is part of this immense living structure. We are not isolated entities, but integral threads in the grand cosmic tapestry. The same gravitational forces that shape the cosmic web also govern the dance of planets around stars, and even the subtle interactions that hold our bodies together. It is a reminder that the universe is not just out there, but deeply intertwined with our very existence. Allow your mind to gently trace these invisible threads, to imagine the silent dance of galaxies drawn towards hidden centers of gravity. Feel the vast emptiness of the voids and the shimmering density of the nodes. In this cosmic web, there is a profound sense of interconnectedness, a quiet harmony that underlies all of existence. It is a vision of the universe as a living, breathing entity, constantly evolving, constantly shaping itself through the elegant interplay of matter, dark matter, and the relentless, gentle pull of gravity. The universe as an emergent phenomenon is consciousness the key. We have gently journeyed through the vastness of space, lingered on the edge of time, and whispered about the hidden architectures of the cosmos. Now, let us turn inward, dear friend, and contemplate a mystery perhaps even more profound and intimately tied to our very existence, the concept of emergence, and the startling idea that consciousness itself might be not just a product of the universe, but perhaps, in some subtle, inexplicable way, a key to its very unfolding. Emergence is a fascinating concept in science. It describes how complex patterns, properties, or behaviors can arise from simpler components, even when those components individually do not possess those complex characteristics. Think of a flock of birds, for example, and each bird follows simple rules, like staying close to its neighbors and avoiding collisions. But from these simple individual actions, a magnificent, complex pattern of flocking behavior emerges. A swirling, coherent entity that seems to have a mind of its own. No single bird has the plan for the whole flock, yet the flock as a whole behaves intelligently. This is emergence. Now, apply this gentle idea to the universe. We often think of the universe as being built from the bottom up, elementary particles combined to form atoms. Atoms form molecules. Molecules form stars and planets, and so on. But what if the grand, intricate laws of physics themselves, the very fabric of space and time, or even the existence of matter and energy, are not fundamental in the way we usually assume? What if they are emergent phenomena, arising from something even more basic, something we haven't yet fully grasped? This is where the idea of consciousness sometimes enters the cosmic conversation. Not as a mystical, unscientific claim, but as a deeply perplexing philosophical question within physics, in quantum mechanics. The very act of observation seems to play a crucial role in determining reality. Before an observation, a quantum particle can exist in a superposition of multiple states simultaneously, a shimmering cloud of possibilities. It is only when an observer, a conscious entity, makes a measurement that the wave function collapses, and the particle settles into a single, definite state. This is known as the measurement problem in quantum mechanics, and it has puzzled physicists for decades. Could this observation-dependent reality extend to the entire universe? Some profound thinkers, stretching back to the early pioneers of quantum mechanics, have pondered whether the universe itself, in its earliest moments, existed in a kind of quantum superposition, a state of indeterminate possibilities, until some form of consciousness, perhaps even a proto-consciousness inherent in the universe itself, emerged to observe it into definitive existence. This is a highly speculative and deeply philosophical idea, far from mainstream scientific consensus. But it highlights the persistent puzzle of consciousness in the grand scheme of things. Consider the implications. If the universe, in some profound sense, requires consciousness to fully actualize its reality, then consciousness wouldn't just be a byproduct of complex biological systems evolving on a planet. Instead, it would be an integral, perhaps even foundational, element of the cosmos itself. This doesn't necessarily mean the universe has a brain or thinks in a human way. It could imply a more subtle, inherent capacity for self-organization and self-awareness that permeates existence at its deepest levels. Some physicists explore what they call information theory as a more concrete way to approach this. They suggest that the universe is fundamentally made of information, not just matter and energy. Information, in this context, is not just data on a computer, it's the fundamental bits that describe reality, the relationships between things. If information is fundamental, and consciousness is inherently tied to processing and interpreting information, then perhaps the emergence of consciousness is not just an accident, but a natural, perhaps even necessary, step in the universe's journey towards ever-increasing complexity and self-organization. Another angle to consider is the anthropic principle, which we briefly touched upon when discussing the multiverse. It states that the universe must be compatible with the existence of intelligent life, because we are here to observe it in its strong form. It takes on a more teleological flavor, suggesting that the universe must evolve consciousness, that it is, in some sense, designed to produce observers. While often criticized for being non-falsifiable and bordering on the metaphysical, it highlights the peculiar alignment of physical constants that allow for life. If even one fundamental constant were slightly different, atoms might not form, stars might not burn, and consciousness would be impossible. Is this just cosmic luck? Or does consciousness play a deeper, more active role in shaping the very laws that allow it to exist? This line of thought resonates with ancient spiritual and philosophical traditions that speak of a universal consciousness, a fundamental awareness from which all reality springs. While science, by its very nature, relies on empirical evidence and testable hypotheses, the contemplation of such ideas, even as thought experiments, can deepen our appreciation for the profound mysteries that lie at the intersection of physics, philosophy, and our own inner experience. What if consciousness is not just in our brains, but a pervasive quality, perhaps dormant or nascent? Within the very fabric of the universe, could the universe itself be slowly waking up through us, through our questions, our observations, our capacity for wonder? This is not to suggest that the universe is a giant thinking being, but perhaps that its capacity for self-organization, for generating complexity and self-awareness, is a fundamental emergent property that has been unfolding since its earliest moments. As you gently drift into these profound thoughts, allow yourself to feel the subtle connection between your own consciousness and the vast, intricate universe outside. The atoms in your brain, the electrical impulses that spark your thoughts, are all part of the same cosmic dance. Your ability to observe, to question, to wonder, is a remarkable manifestation of the universe's own unfolding complexity. In this quiet realization, there is a deep, comforting sense of belonging, a feeling that your inner world is intimately connected to the grand tapestry of existence. Let these ideas gently settle. Like soft rain on quiet earth, there is no need for certainty, no pressure to find immediate answers. Simply allow your mind to wander, to explore the beautiful, perplexing possibilities that lie at the heart of reality. The universe, in its boundless mystery, continues to invite our gentle inquiry, our quiet wonder, and our profound contemplation. The universe as an emergent phenomenon is consciousness the key. Tie up, Theo. We continue our quiet, reflective journey. Dear friend, into the deepest questions about existence. We have gently stepped into the intriguing world of emergence, where complex patterns and properties arise from simpler, underlying components. And we've dared to whisper about the profound idea that consciousness might be more than just a happenstance byproduct of biological evolution. Could it be, in some subtle and perhaps still unfathomable way, integral to the very fabric and unfolding of the universe itself? This is a realm where the certainties of science gently blur with the vast, shimmering possibilities of philosophy. Recall the simple elegance of a flock of birds. Individually, each bird follows a few basic rules, yet, collectively, they create a mesmerizing, complex dance in the sky. No single bird holds the blueprint for the entire formation, but the harmonious, intelligent behavior of the flock emerges from the sum of its simpler parts. This is emergence. Now, extend this gentle concept to the cosmos itself. We typically perceive the universe as a grand construction built from the bottom-up elementary particles combined to form atoms. Atoms coalesce into molecules, which in turn form stars, planets, and galaxies. But what if the profound, intricate laws of physics themselves, the very dimensions of space and time, and even the fundamental existence of matter and energy, are not as fundamental as we conventionally assume? What if they, too, are emergent phenomena, arising from something even more foundational, something we are only just beginning to grasp. This is where the notion of consciousness sometimes enters the cosmic conversation, not as a leap into mysticism, but as a deeply perplexing and persistent philosophical question that has quietly lingered at the edges of physics, especially quantum mechanics. In the strange and wonderful world of quantum mechanics, the very act of observation appears to play a uniquely crucial role in shaping reality. Before an observation is made, a quantum particle, say an electron, can exist in a superposition of multiple possible states simultaneously. It is not here or there, but a shimmering cloud of possibilities, occupying all potential locations at once. It is only when an observer, a conscious entity with the capacity to measure or interact, makes a measurement that the particle's wave function collapses, and it chooses a single, definite state. This measurement problem in quantum mechanics has baffled and fascinated physicists for nearly a century, suggesting a peculiar and unsettling link between mind and matter. Could this observation-dependent reality extend beyond the tiny quantum realm to encompass the entire universe? Some profound thinkers, tracing their lineage back to the very pioneers of quantum mechanics like John Archibald Wheeler, have quietly pondered whether the universe itself, in its earliest, most indeterminate moments, might have existed in a kind of cosmic quantum superposition, a vast, shimmering ocean of indeterminate possibilities, waiting to be observed into definitive existence. And if so, what kind of consciousness or proto-consciousness might have emerged? Perhaps inherently intertwined with the universe's own unfolding. To perform this cosmic observation, this is, without doubt, a highly speculative and deeply philosophical idea. Far from the established consensus of mainstream scientific thought, yet it serves to illuminate the persistent, challenging puzzle of consciousness's place within the grand, overarching narrative of the cosmos. Consider the profound implications of such an idea. If the universe, in some fundamental, inexplicable way, requires consciousness to fully actualize its reality, then consciousness would cease to be merely a happenstance byproduct of complex biological systems evolving on a random planet. Instead, it would be elevated to an integral, perhaps even foundational, element of the cosmos itself. This doesn't necessarily imply that the universe possesses a brain in the human sense, or that it thinks with human-like cognition. Rather, it could suggest a more subtle, inherent capacity for self-organization, for self-awareness, that quietly permeates existence at its deepest, most primordial levels. Some physicists explore this mystery through the lens of information theory, proposing a more concrete, albeit still abstract, approach. They suggest that the universe is not fundamentally made of matter and energy alone, but is, at its core, comprised of information. Information, in this context, is far more than just data stored on a computer. It is the fundamental bits that describe reality, the intricate relationships between things, the very patterns that define existence. If information is indeed fundamental, and consciousness, by its very nature, is inextricably tied to the processing, interpreting, and generating of information, then perhaps the emergence of consciousness is not merely an accident or a lucky roll of cosmic dice. Instead, it might be a natural, perhaps even necessary, step in the universe's ceaseless journey towards ever-increasing complexity and self-organization. The universe, in this view, is constantly processing its own information, and we, as conscious beings, are a part of that grand, unfolding computation. Another perspective, offering a slightly different nuance, comes from the anthropic principle, which we briefly touched upon when discussing the vast possibilities of the multiverse. The weak anthropic principle simply states that the universe must be compatible with the existence of intelligent life because Well, we are here to observe it. It's a statement of selection bias. However, the strong form of the anthropic principle takes on a more profound, almost teleological, flavor. It suggests that the universe must evolve consciousness, that it is, in some sense, inherently designed or compelled to produce observers. While this stronger version is often critiqued for being non-falsifiable and for bordering on the metaphysical, it undeniably highlights the peculiar and extraordinary fine-tuning of fundamental physical constants that are absolutely essential for life to exist. If even one fundamental constant, the strength of gravity, the mass of an electron, the precise value of the cosmological constant were minutely different, atoms might not form, stars might not burn, and the intricate dance of chemistry that leads to life would be utterly impossible. Is this just an astonishing stroke of cosmic luck? A lottery win against impossible odds, or does consciousness, or its potential, play a deeper, more active role in subtly shaping the very laws that allow it to exist? This profound line of thought resonates with ancient spiritual and philosophical traditions from across cultures and millennia. Traditions that speak of a universal consciousness, a fundamental awareness or ground of being from which all reality, all phenomena, ultimately spring, while empirical science, by its very nature, rigorously relies on observable evidence and testable hypotheses. The gentle contemplation of such ideas, even as pure thought experiments, can profoundly deepen our appreciation for the immense, beautiful mysteries that lie at the intricate intersection of physics, philosophy, and our own inner, subjective experience. What if consciousness is not just confined to our individual brains, those intricate neural networks within our skulls, but is a more pervasive quality, perhaps dormant or nascent? Within the very fabric of the universe itself, could the universe, in its grand, slow unfolding, be gradually waking up through us, through our ceaseless questions, our meticulous observations, our profound capacity for wonder and self-reflection? This is not to suggest that the universe is a giant thinking being, like a cosmic brain with intentions and desires. Instead, it might imply that the universe's inherent capacity for self-organization, for generating ever-increasing layers of complexity, and for ultimately producing self-awareness, is a fundamental, emergent property that has been gently unfolding since its earliest, most primordial moments. The universe, in this view, is not just evolving, but also becoming aware of its own evolution through the beings it gives rise to. As you gently drift into these profound thoughts, allow yourself to feel the subtle, undeniable connection between your own consciousness and the vast, intricate universe that surrounds and permeates you. The very atoms that compose your brain, the delicate electrical impulses that spark your thoughts, the chemical reactions that allow you to feel and perceive all are part of the same grand cosmic dance. Your remarkable ability to observe, to question, to wonder, to feel. This is a truly astonishing manifestation of the universe's own unfolding complexity, a testament to its boundless creativity. In this quiet realization, there's a deep, comforting sense of belonging, a feeling that your inner world, your consciousness, is intimately and inextricably connected to the boundless, evolving tapestry of existence. Let these ideas gently settle in your mind, like soft moonlight filtering through quiet leaves, casting intricate shadows on the path below. There is no need for immediate answers, no pressure to find definitive conclusions. Simply allow your mind to wander, to explore the beautiful, perplexing possibilities that reside at the very heart of reality. The universe, in its boundless mystery, continues to invite our gentle inquiry, our quiet wonder, and our profound contemplation. It asks us to look both outward, into the starry depths, and inward, into the mysterious depths of our own awareness. For perhaps the deepest answers lie at the convergence of these two boundless realms, the quantum foam. Where reality shimmers and dissolves, let us now gently venture. Dear friend, into a realm so tiny, so fleeting, that it challenges our very notion of what empty space truly is. We've spoken of grand cosmic structures, of galaxies and the vast stretches of time. Now, we will whisper about the quantum foam, a concept that suggests reality, at its most fundamental level, is not smooth and predictable, but a seething, shimmering chaos of fleeting particles and fluctuating fields. It is here, at the Planck scale, the smallest meaningful scale in the universe, that the very fabric of space and time begins to shimmer and dissolve. Revealing a deeper, more ephemeral reality, imagine, if you will, the seemingly empty space around you. We often perceive it as a void, a silent, unchanging backdrop for the drama of matter and energy. But in the strange and wondrous world of quantum mechanics, emptiness is never truly empty. Instead, it is a bustling, effervescent sea of activity. This is the quantum vacuum, and it is anything but silent. It is a frothing, bubbling cauldron where virtual particles constantly pop into existence and vanish in an instant. Like tiny, ephemeral bubbles rising and bursting on the surface of a cosmic ocean. These particles are virtual because they exist for such an unimaginably short time that they cannot be directly observed. They appear and disappear in pairs, a particle and its antiparticle, borrowing energy from the vacuum for a fleeting moment, only to return it almost immediately. Respecting the universe's strict energy accounting, this continuous creation and annihilation of virtual particles is a fundamental aspect of quantum field theory, and it means that even the emptiest space is seething with unobserved, fleeting energy. Now, extend this idea to the very fabric of space-time itself, at the unimaginably small scales, far, far below the size of an atom, below even the nucleus of an atom, below the realm of quarks and leptons, lies the Planck scale. This is the scale where the two great pillars of modern physics, quantum mechanics and general relativity, both become critically important. Quantum mechanics governs the behavior of particles at tiny scales, while general relativity describes gravity and the curvature of spacetime at large scales. However, neither theory, in its current form, can fully describe what happens when you combine the two at these extreme limits. This is precisely where the concept of quantum foam emerges, proposed by physicist John Archibald Wheeler. The idea of quantum foam suggests that at the Planck scale, spacetime itself is not smooth and continuous, but rather turbulent and discontinuous. It's as if, when you zoom in close enough, the smooth fabric of spacetime unravels into a chaotic, bubbling mess of constantly changing topology. Imagine the surface of a boiling pot of water, constantly forming and collapsing bubbles, its surface never truly still. The quantum foam is a similar, but far more abstract phenomenon occurring in the very structure of reality. At this scale, space-time itself is thought to fluctuate wildly. Tiny, ephemeral wormholes might constantly appear and disappear, briefly connecting distant regions of space and time. Miniature black holes might spontaneously form and evaporate. The very dimensions we experience up-down, left-right, forward-backward, and the flow of time might lose their distinct identity, becoming tangled and interconnected in a chaotic, probabilistic dance. It's a realm where the familiar notions of distance and duration simply cease to be meaningful in any conventional sense. The universe, at its most fundamental level, is not a solid, static foundation, but a shimmering, constantly reconfiguring quantum froth. This idea has profound implications for our understanding of reality and the nature of the universe's origin. If space and time are emergent properties, arising from this deeper quantum foam, then the Big Bang singularity, The point of infinite density and curvature might be replaced by a gentler transition, instead of a point where physics breaks down. The quantum foam could provide a bridge through which the universe passed, perhaps from a previous contracting phase into our current expanding one. As suggested by loop quantum cosmology, the singularity would be smeared out by quantum effects, replaced by a minimum size where the quantum nature of gravity takes over. The quantum foam also poses immense challenges for observation. The Planck length, the characteristic scale of this foam, is incredibly small, approximately 10^35 meters. To give you a gentle sense of its tininess, imagine shrinking an atom to the size of the entire observable universe. A Planck length would be roughly the size of that atom in comparison. Detecting phenomena at such scales is far beyond any current or foreseeable technology. We cannot simply build a microscope powerful enough to peer into the quantum foam instead. Physicists must rely on indirect evidence, looking for subtle fingerprints of this underlying quantum reality in phenomena at much larger scales, such as in the cosmic microwave background or in the behavior of gravitational waves. Despite the observational difficulties, the concept of quantum foam is crucial for developing a complete theory of quantum gravity, both string theory and loop quantum gravity. The leading candidates for such a theory attempt to describe the universe at these fundamental scales. String theory suggests that at the Planck length, particles are not point-like, but rather tiny, vibrating strings, and that space-time itself arises from the interactions of these strings. Loop quantum gravity, as we've discussed, proposes that space-time is quantized into discrete loops. Both theories offer different visions of the quantum foam, but they share the common goal of reconciling gravity with quantum mechanics, thereby providing a more complete picture of reality at its most ephemeral depths. As you gently contemplate the quantum foam, imagine a reality that is constantly being created and dissolved, a universe that is never truly still, even in its deepest, most hidden corners. This is a realm where certainty gives way to probability, where solidity dissolves into shimmering possibilities, and where the very essence of existence is a dynamic, effervescent dance. It is a reminder that what we perceive as stable and unchanging is, at a more fundamental level, a breathtakingly active and fluid reality. Allow this profound idea to settle in your mind, like the gentle, almost imperceptible hum of distant stars. There is a deep, quiet comfort in realizing that even emptiness is full of potential, that even silence is brimming with unseen activity. The quantum foam, though beyond our direct grasp, invites us to embrace a universe that is far more wondrous and mysterious than our everyday senses can perceive. It encourages us to let go of rigid expectations and to simply wonder at the ceaseless, beautiful dance of existence, right down to its most ephemeral threads. The landscape of string theory, a symphony of possibilities now. Let us float on, dear friend, from the turbulent quantum foam to a grander, more expansive vision, the landscape of string theory. This concept paints a picture of a universe far vaster and more diverse than we once imagined, a multiverse of almost unimaginable possibilities, where our familiar reality is but one tiny valley in an immense, cosmic mountain range. It is a thought that invites both wonder and a gentle humility, reminding us of the boundless creativity of existence. For decades, physicists have sought a single, elegant theory of everything, a unified framework that could describe all fundamental forces and particles in the universe. String theory emerged as a leading candidate. At its heart, string theory proposes that the most fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, one-dimensional vibrating strings. Imagine a violin string depending on how it vibrates. It produces different musical notes. Similarly, in string theory, different vibrational modes of these fundamental strings give rise to different particles, such as electrons, quarks, photons, and even gravitons, the hypothetical particles that carry the force of gravity. This elegant idea beautifully unifies all particles and forces under a single, vibrating symphony. However, for string theory to work mathematically, it requires the existence of extra spatial dimensions beyond the three familiar dimensions of space: up, down, left, right, forward, backward, and one dimension of time that we experience. These extra dimensions are not large and easily visible. Instead, they are thought to be compactified or curled up into incredibly tiny, intricate shapes, far too small for us to detect directly. Imagine a hose pipe from a distance. It looks like a one-dimensional line, but up close, you see it has a second, curled up dimension, its circular circumference. Similarly, these extra dimensions in string theory are curled up in complex ways at every point in our familiar three-dimensional space. The crucial insight that led to the concept of the landscape is that there are an enormous number of ways these extra dimensions can be curled up. Imagine a colossal, intricate origami folded in countless different patterns. Each distinct way of compactifying these extra dimensions gives rise to a different vacuum state of the universe. And each vacuum state, in turn, corresponds to a different set of physical laws and constants. For example, in one way of curling up the extra dimensions, the electron might have a certain mass. In another, it might have a slightly different mass. In one vacuum state, the force of electromagnetism might be a certain strength. In another, it could be slightly weaker or stronger. The number of possible ways to compactify these extra dimensions is truly astronomical. Estimates range from 10^500 to even more, an unimaginably vast number, far greater than the number of atoms in the observable universe. Each of these distinct compactifications represents a different valley in a metaphorical landscape of possibilities. Our universe, with its specific values for physical constants and its particular set of physical laws, would simply be one tiny, unique valley within this immense, cosmic landscape. This is the string theory landscape, a vast, multi-dimensional space where each point represents a possible universe, each with its own unique physics. This concept has profound implications for the search for a unique theory of everything. If there are 10^500 possible universes, then string theory might not predict a single, unique outcome for the laws of physics. Instead, it might predict an immense array of possible universes, each consistent with the fundamental principles of string theory. This raises the question, why are we in this particular valley? Why do our physical constants have precisely the values they do? Values that seem so perfectly fine-tuned for the existence of life. This is where the multiverse concept, often linked with eternal inflation, which we gently touched upon earlier, re-enters the conversation. If eternal inflation is indeed at play, it would constantly be creating new bubble universes, each potentially settling into a different one of the 10^500 vacuum states predicted by the string theory landscape. Our universe would simply be one of these bubbles. Perhaps one of the fortunate ones where the physical constants happen to be just right for stars to form, for complex chemistry to arise, and for consciousness to emerge and ponder these very questions. The anthropic principle finds a natural home here. We observe the universe we do, because it's the only kind of universe in which observers like us could exist. This idea challenges the traditional notion of a single, unique universe governed by a uniquely derived set of laws. Instead, it suggests a cosmic abundance, an infinite variety of realities quietly unfolding, each a slightly different symphony played on the strings of existence. It shifts the question from why is our universe like this to given an infinite number of universes. What kind of universe would we expect to find ourselves in, given that we exist? While the string theory landscape offers a compelling framework for understanding the apparent fine-tuning of our universe, it also faces significant challenges. The sheer number of possible vacua makes it incredibly difficult to make testable predictions specific to our universe. How do we distinguish our valley from countless others without direct observational access to them? This is a fundamental scientific hurdle. Furthermore, the landscape concept has sparked considerable debate. Is it truly a scientific theory if it doesn't uniquely predict our universe? Or is it a powerful framework for understanding cosmic diversity, even if it introduces the notion of a multiverse? As you gently allow these thoughts to settle, imagine the universe not as a single, isolated melody, but as an infinite cosmic orchestra, each instrument playing a slightly different tune, each note a unique possibility. Our own universe, with its specific laws and beautiful complexity, is but one precious song in this grand, boundless symphony. The landscape of string theory invites us to embrace a vision of reality that is far richer, more varied, and more creative than we might have ever dared to imagine. In this vast cosmic landscape, there is a profound sense of humility, but also a quiet liberation. The universe is not bound by a single, rigid set of rules, but thrives in an almost unimaginable abundance of possibilities. And in knowing this, we can find a deep, comforting peace, a sense that existence itself is an endlessly unfolding tapestry of wonder, far grander than any single story could ever tell. The multiverse beyond our cosmic bubble. Let us now, dear friend, gently stretch our minds even further, beyond the familiar confines of our own universe, to explore a concept both grand and deeply unsettling: the multiverse. Imagine our universe, with its billions of galaxies and its intricate laws of physics, as but a single bubble in an endlessly frothing, cosmic ocean. This ocean, teeming with countless other bubbles, each a universe unto itself. Is the multiverse? It is a concept that challenges our deepest intuitions about uniqueness and opens up a breathtaking panorama of infinite possibilities. The idea of a multiverse isn't merely a flight of fancy. It arises quite naturally from several leading scientific theories we've gently touched upon. One of the most compelling origins for the multiverse lies within the theory of eternal inflation. We previously imagined inflation as a period of incredibly rapid, exponential expansion right after the Big Bang, smoothing out our universe and setting the stage for galaxy formation. But in many inflationary models, this process doesn't simply stop everywhere at once. Instead, it continues indefinitely in some regions of space, endlessly budding off new bubble universes where inflation does end, giving rise to familiar cosmic conditions. Picture a vast cosmic foam. In some parts of this foam, the underlying energy field driving inflation is still actively pushing space apart at an accelerating rate, creating more and more space. But occasionally, in random pockets within this eternally inflating expanse, the field settles down, causing inflation to cease. These pockets then thermalize, filling with hot matter and radiation, effectively becoming new Big Bangs, new universes. Like ours, because the space between these bubbles is still inflating furiously. These universes are causally disconnected from each other. They cannot interact. They cannot exchange light or information, making them truly separate realities. Our universe, then, is simply one such bubble, floating in an infinite ocean of others. The profound implication of this model is that each of these bubble universes could have slightly, or even drastically, different properties. Remember the string theory landscape. That vast array of possible ways the extra-spatial dimensions could be curled up, each corresponding to a different set of physical laws and constants. Eternal inflation provides a mechanism to populate that landscape. Each newly formed bubble universe might randomly choose a different configuration of these curled-up dimensions, thereby settling into a different vacuum state with its own unique physical laws. In one universe, gravity might be stronger in another. The mass of the electron might be different in yet another. There might be different fundamental particles altogether. The possibilities are truly astronomical, extending beyond what our human minds can easily grasp. This leads us back to the anthropic principle. But now, with a grander cosmic stage, if there are infinitely many universes, each with a different set of physical laws, then it's no longer so surprising that our universe has precisely the finely tuned properties necessary for life. We simply happen to find ourselves in one of the universes where conditions are just right for stars to form, for complex chemistry to emerge, and for sentient beings like us to evolve and ponder the cosmos. If our universe had slightly different constants, for example, the nuclear forces were a tiny bit weaker, or the electromagnetic force a bit stronger, atoms might never form, or stars might burn out too quickly, making life impossible? We wouldn't be here to observe such a universe. The multiverse, in this view, offers a powerful, albeit non-falsifiable, explanation for the apparent lucky draw of our cosmic parameters beyond eternal inflation. Other ideas also hint at a multiverse. M-theory, a broader framework that encompasses all 5 consistent string theories, sometimes suggests that our universe might be just one brain, a higher dimensional membrane floating in a higher dimensional bulk space. Other brains, representing other universes, could exist parallel to ours, perhaps occasionally brushing against each other, causing subtle ripples that might leave imprints on our own reality. Such brain collisions could even be the origin of Big Bangs, leading to a cyclic multiverse where universes are continuously born from the echoes of previous collisions. Then there is the concept of the many worlds interpretation of quantum mechanics. While not a cosmological multiverse in the same spatial sense, it proposes a different kind of multiplicity. It suggests that every time a quantum measurement is made, every time a wave function collapses, the universe literally splits into multiple parallel realities, each representing a different outcome of that measurement in one branch. The electron spins up, in another, it spins down. If this is true, then an unimaginably vast, constantly branching quantum multiverse is being created every fleeting moment. With every quantum interaction, this is a multiverse of possibilities, where every decision, every chance event, leads to an entire new universe splitting off. The implications of the multiverse are profound and far-reaching. It shifts our perspective from a singular, unique creation to an unimaginably rich and varied tapestry of realities. It suggests that the true universe is not just the one we observe, but this boundless collection of all possible universes. This can be both humbling and strangely liberating. Humbling, because it places our familiar cosmos in a tiny, perhaps unexceptional corner of a much grander stage. Liberating, because it frees us from the need to find a single, ultimate explanation for every peculiar feature of our reality. Those features might just be the accidental properties of our particular bubble. Of course, the multiverse concept faces significant scientific and philosophical challenges. The most prominent is its testability. How can we ever truly prove the existence of other universes if they are, by definition, causally disconnected from ours? How can we gather empirical evidence for something we cannot see, touch, or measure? While subtle fingerprints like bubble collision, imprints in the CMB are theoretically possible, they remain elusive. This lack of direct testability leads some scientists to view the multiverse as more of a philosophical concept than a falsifiable scientific theory. However, many physicists argue that if the multiverse arises inevitably from our most successful theories, such as eternal inflation, then we should consider it a serious scientific hypothesis. Even if direct proof is currently out of reach, it is a natural extension of our understanding, a logical consequence of the very frameworks we use to describe our own universe. The discussion continues, a vibrant dialogue at the cutting edge of human knowledge. As you gently rest with these thoughts, imagine the vastness not just of space but of realities. See our universe as a vibrant, unique bubble, shimmering amidst an infinite cosmic foam. Feel the quiet hum of possibilities, the countless other cosmic stories unfolding alongside our own. There is a deep, comforting peace in realizing that existence itself is so incredibly abundant, so endlessly creative, that it manifests in ways far beyond our singular comprehension. Let this expansive vision settle in your mind, like distant starlight finally reaching quiet eyes. The multiverse. Whether a literal reality or a powerful metaphor for infinite possibility, invites us to embrace a universe that is far grander, far more mysterious, and infinitely more awe-inspiring than we could ever have dreamt. In its boundless embrace, we find a profound sense of wonder, a quiet call to simply be, to breathe, and to marvel at the ceaseless, beautiful unfolding of all that is. The holographic principle is reality, a cosmic projection. Let us now, dear friend, embark on an even more ethereal journey, one that challenges our fundamental understanding of reality itself. Imagine the world around you, filled with vibrant colors, solid objects, and the vast expanse of space. What if all of this, every star, every galaxy, every atom, even you and I, are merely projections? What if the seemingly three-dimensional reality we inhabit is actually encoded on a distant, two-dimensional surface, much like a hologram? This profound and mind-bending idea is known as the holographic principle, and it is one of the most radical, yet compelling concepts to emerge from the quest for a theory of quantum gravity. The holographic principle suggests that the information describing a volume of space can be entirely contained on its boundary, a surface with one less dimension. Think of a credit card hologram. It's a two-dimensional image, yet when light reflects off it in a certain way, it creates the illusion of a three-dimensional object floating in space. The holographic principle posits something similar for the entire universe. Our three-dimensional reality might be a mere illusion, a detailed projection from information stored on a two-dimensional cosmic boundary, perhaps at the very edge of our observable universe, or even on a much deeper, more fundamental level. This idea first emerged from the study of black holes. When we consider black holes, those enigmatic cosmic devourers, we encounter a perplexing problem related to information. According to classical physics, anything that falls into a black hole is seemingly lost forever. However, quantum mechanics dictates that information can never be truly destroyed. This conflict led to what's known as the black hole information paradox. Stephen Hawking's groundbreaking work on Hawking radiation suggested that black holes slowly evaporate over immense timescales, emitting a faint thermal glow. But what happens to the information of the matter that fell in if the black hole simply evaporates? The information would be gone, violating a fundamental quantum principle. This is where the holographic principle offers a tantalizing solution. Jacob Bekenstein and later Stephen Hawking demonstrated that the entropy of a black hole, a measure of its disorder and thus its information content, is proportional not to its volume, but to the area of its event horizon, the point of no return beyond which nothing, not even light, can escape. This was a profound and counterintuitive discovery. If the information of everything that falls into a black hole is encoded on its two-dimensional surface, rather than within its three-dimensional volume, then perhaps the information paradox could be resolved. The information isn't destroyed, it's simply stored on the boundary. This seemingly esoteric finding about black holes sparked a radical generalization if it holds true for black holes. Could it hold true for the entire universe? Leonard Susskind and Gerard de Hooft formalized this into the holographic principle for the cosmos. It implies that the total amount of information contained in a region of space is bounded by the area of its boundary, not its volume. If this is correct, then everything we experience in our three-dimensional world, every intricate detail, every subtle interaction could be fundamentally described by a set of bits of information residing on a distant, two-dimensional surface. Our reality would be like a cosmic movie projected from a flat reel. One of the most concrete examples of the holographic principle in action comes from the anti-de Sitter space conformal field theory, ADS CFT correspondence. Proposed by Juan Maldacena, this is a powerful duality that demonstrates a mathematical equivalence between certain quantum field theories living in a specific type of spacetime called anti-de Sitter space, which has a negative curvature. Unlike our universe's nearly flat geometry and a theory of gravity living in one higher dimension. In simpler terms, it shows that a specific kind of gravity in a higher dimension is exactly equivalent to a quantum field theory with no gravity in a lower dimension. This mathematical bridge strongly suggests that a holographic relationship is indeed possible, where information about gravity in one dimension can be perfectly described by a non-gravitational theory on a lower dimensional boundary, while Adias's space is not precisely our universe. The Adias CFT correspondence provides a powerful theoretical laboratory for exploring the implications of the holographic principle. The implications of the holographic principle are truly mind-bending. If our reality is a projection, it suggests that the fundamental nature of existence is not what it appears to be. The solidity, the depth, the very spatial dimensions we perceive might be emergent properties, arising from a more fundamental, two-dimensional information-rich surface. It might mean that the universe, at its core, is a vast information processing system, and that consciousness, in its deepest sense, is intimately tied to the decoding and experience of this projected information. This concept also has subtle connections to the idea of a digital universe or a simulated reality. If reality is ultimately information encoded on a surface, one could, in theory, imagine a sufficiently advanced civilization or a cosmic intelligence creating such a projection. While this takes us further into the realm of philosophy and science fiction, the holographic principle provides a concrete physics framework that hints at such possibilities. It raises questions about what is truly real and what is merely a manifestation of underlying information. How could we ever test such a radical idea? This is where the challenges become immense. One speculative approach involves looking for subtle fuzziness or pixelation in spacetime at extremely small scales. Much like zooming in on a digital image reveals its individual pixels, these quantum pixels might manifest as tiny, almost imperceptible distortions or noises in spacetime. Some experiments, like the GEO 600 gravitational wave detector, have explored whether such quantum effects could be detected, though no definitive evidence has yet been found. Another avenue involves examining the cosmic microwave background for peculiar patterns that might reveal underlying two-dimensional information encoding, or investigating whether there are limits to how much information can be stored in a region of space. These are incredibly subtle effects, requiring extraordinary precision and sensitivity as you gently immerse yourself in the thought of the holographic principle. Imagine a universe that is a grand, cosmic illusion, a breathtaking projection generated from an unseen source. Feel the subtle shift in perspective, where solidity gives way to information, and depth to surface. There is a deep, quiet wonder in contemplating a reality far more intricate and mysterious than our everyday senses can perceive. Let this profound concept settle in your mind. Like distant starlight reflecting on a still lake, there is a comforting sense of elegance in the idea that complexity can arise from simplicity, that a rich, vibrant reality can be painted from a fundamental, encoded canvas. The holographic principle invites us to embrace a universe that is not just vast in space and time, but also profound in its very nature, a cosmic secret waiting to be gently unveiled. In this contemplation, we find a renewed sense of awe for the boundless creativity of existence, and a quiet appreciation for the exquisite mystery of what truly is. The simulation hypothesis. Are we living in a designed reality? Let us now, dear friend, continue our gentle exploration into the deepest philosophical and scientific questions about the nature of reality. We've just touched upon the holographic principle, The idea that our three-dimensional universe might be a projection from a two-dimensional surface. Building upon this, we now delve into an even more provocative and utterly mind-bending concept, the simulation hypothesis. What if everything we experience, every thought, every feeling, every interaction, every star in the sky, every atom in our bodies, is part of an incredibly sophisticated computer simulation? What if our entire reality is a painstakingly crafted virtual world, running on hardware far beyond our comprehension? This idea is not new. It has been pondered by philosophers for centuries, from Plato's allegory of the cave to René Descartes' evil demon. But in recent decades, with the rapid advancement of computing power and our understanding of physics, the simulation hypothesis has gained traction as a serious, albeit still highly speculative, scientific and philosophical argument. One of the most articulate proponents of the simulation hypothesis is the philosopher Nick Bostrom. He proposed a trilemma, a three-part argument, suggesting that at least one of the following three propositions must be true. Civilizations almost never reach a technological maturity that allows them to run high-fidelity ancestor simulations. Perhaps every advanced civilization destroys itself before reaching that point. Or maybe there are fundamental physical limits to computing power that make such simulations impossible. Technologically mature civilizations are almost never interested in running ancestor simulations, even if they could. Perhaps they find it ethically problematic, or simply boring, or they have other priorities. We are almost certainly living in a simulation. If it's possible for civilizations to reach this level of technological maturity, and they are interested in running such simulations, then, given the sheer number of simulated realities they could create, the probability that we are in the original base reality becomes astronomically small. It would be like drawing a single lottery ticket from an infinite pile. The core of the argument rests on the assumption that as computing power advances, it will eventually become feasible to create simulations that are indistinguishable from reality for their inhabitants. If a civilization can run one such ancestor simulation, a highly detailed simulation of their historical past, they could run millions, billions, or even trillions of them. Each simulated reality would contain simulated conscious beings, who would then themselves ponder the nature of their reality. Given enough time and technological progress, the number of simulated realities would vastly outnumber the single base reality, making it overwhelmingly probable that any given conscious observer like us exists within a simulation rather than the original. Unsimulated universe. What are the implications if this hypothesis were true? It would mean that the laws of physics we observe might not be the true fundamental laws of the universe, but rather the programmed rules of our simulation. These rules might be incredibly sophisticated, designed to mimic fundamental physics with astonishing accuracy, or they might contain subtle glitches or Easter eggs that could, theoretically, hint at their simulated nature. Some physicists have even playfully suggested looking for anomalies in cosmic ray energies or subtle limits to physical calculations that might betray the processing power of the underlying simulator. The simulation hypothesis also touches upon the nature of consciousness. If we are simulated beings, does our consciousness arise from the code of the simulation? Or is it something external that plugs into the simulation? This leads to fascinating philosophical questions about the nature of identity, free will, and the very essence of what it means to be alive. If our reality is simulated, could the simulators be entities far beyond our comprehension? Perhaps even gods in our traditional sense. And what would be their purpose in running such a simulation? Could it be for research, entertainment, or something entirely alien to our understanding? This idea connects quite profoundly with the holographic principle we just discussed. If reality is a projection from a lower dimensional surface, this structure could be seen as an incredibly efficient way to store and render a simulated universe. The bits of information on the two-dimensional boundary could be the very data points that describe our projected three-dimensional reality. The universe, then, would be a giant, living computer program, constantly running and updating. Of course, the simulation hypothesis faces immense challenges. How could we possibly test it? Any evidence we find within the simulation could potentially be programmed into it. It's difficult to find external evidence when you are, by definition, internal to the system. While some propose looking for computational limits, like a pixelated spacetime at the Planck scale, echoing the holographic principle, or numerical instabilities in cosmic phenomena. These are highly speculative and have not yielded conclusive results. Furthermore, the hypothesis doesn't directly solve the question of ultimate origins. It simply pushes the problem one level up who simulated the simulators. This leads to an infinite regress, which some find unsatisfactory. Despite these challenges, the simulation hypothesis serves as a powerful thought experiment. It forces us to question our assumptions about reality, to consider that our everyday perceptions might not reveal the full truth of existence. It encourages a deeper humility about the limits of human knowledge and the possibility that the universe is far more intricate and layered than we currently understand. It's a reminder that what we deem real is often just what our current tools and senses allow us to perceive. As you gently allow these thoughts to settle, imagine the universe as a grand, intricate piece of code, flawlessly executed by an unseen intelligence. Feel the subtle tremor of possibility, the notion that your very thoughts are part of a cosmic algorithm. Unfolding in real time, there is a deep, quiet wonder in contemplating a reality that might be both profoundly engineered and exquisitely beautiful. Let this concept softly linger in your mind, like the faint hum of distant cosmic machinery. There is no need for alarm, no call for existential dread. Instead, find a strange, comforting peace in the boundless creativity that such a hypothesis suggests. The simulation hypothesis, whether literal or metaphorical, invites us to embrace a universe that is far more mysterious, far more ingenious, and infinitely more awe-inspiring than our linear minds might ever grasp. In its gentle embrace, we find a renewed sense of curiosity, a quiet invitation to simply marvel at the intricate, unfolding layers of all that is the nature of reality, from the quantum to the cosmic. Let us now, dear friend, bring together the many threads of our gentle cosmic journey. We've traversed immense distances, from the subatomic shimmer of quantum foam to the vast, fractal expanse of the cosmic web. We've dared to peer into the universe's ultimate end and pondered the profound possibility that our reality might be a mere projection or even a grand simulation. As we gather these diverse insights, a deeper question softly emerges. What, then, is the true nature of reality? Is it solid, definite, and external to us? Or is it more fluid, intertwined with observation, and perhaps even emergent from consciousness itself? Our journey began with the familiar. We spoke of the Big Bang, that fiery genesis which set the cosmic clock ticking, and how the cosmic microwave background CMB offers us a faint, ancient whisper from that primordial time. We understood that the universe is expanding, accelerating outward, driven by the enigmatic dark energy, leading to potential fates like the Big Freeze, Big Crunch, or Big Rip. These scenarios, while vast in scale, are rooted in our understanding of gravity and matter, painting a picture of a universe governed by well-defined physical laws, evolving from a clear beginning to a predicted end. Yet, as we delved deeper, the solidity of that picture began to gently soften. We encountered the Planck scale, where the very concepts of space and time begin to lose their meaning. Here, the quantum foam suggests a reality that is turbulent and chaotic, a ceaseless dance of virtual particles and fluctuating spacetime. This challenges the notion of a perfectly smooth, static backdrop. revealing instead a dynamic, effervescent, and fundamentally uncertain foundation for all that exists. It hints that empty space is anything but empty, bustling with potential and fleeting existence from this quantum realm. We explored the idea that the Big Bang singularity might be an illusion, a point where our classical theories break down, rather than an ultimate beginning. Concepts like the Big Bounce from loop quantum gravity propose a universe that contracts and then rebounds, smoothly transitioning through a phase of extreme density without ever hitting an infinite singularity. In this view, our universe is but one chapter in an endless, cyclical cosmic story, a continuous dance of expansion and contraction, driven by the quantum nature of gravity itself. Here, geometry, rather than matter or energy, might be the most fundamental aspect of reality. Then, we expanded our gaze to the multi-layered possibilities presented by eternal inflation and the string theory landscape. This suggested that our universe might not be unique, but one among countless bubble universes, each with its own set of distinct physical laws and constants. This multiverse concept, while difficult to test directly, offers a compelling explanation for the apparent fine-tuning of our universe's parameters, suggesting that our existence is simply a matter of probabilities within an infinite cosmic lottery. It challenges the idea of a singular, specially chosen reality, offering instead a vast tapestry of diverse possibilities. Finally, we ventured into the most thought-provoking concepts, the holographic principle and the simulation hypothesis. The holographic principle posits that our three-dimensional reality might be a projection from a two-dimensional surface, implying that the universe is fundamentally a vast information system. Building on this, the simulation hypothesis takes the idea even further, suggesting that our entire perceived reality could be an incredibly sophisticated computer simulation. These ideas, while speculative, force us to question the very nature of realness and whether our perceptions truly reveal ultimate truth. They hint at a reality where information, rather than matter or energy, is the most fundamental constituent, and where even our most cherished physical laws might be emergent rules of a grand cosmic program. So, what does this multifaceted journey tell us about the nature of reality? Reality is far more complex than it appears. Our everyday experience of a solid, stable, three-dimensional world, flowing through linear time, is likely just one layer of a far deeper, more intricate, and dynamic reality. What appears empty is teeming with quantum activity, and what seems solid might be a projection of information. The limits of our perception. We are inherently limited by our senses and our current scientific instruments. The Planck scale, the nature of dark energy, the existence of other universes, these realms often lie beyond our direct grasp. We must infer their existence from indirect evidence and extrapolate from our best theories. The interconnectedness of everything. From the cosmic web, where gravity weaves galaxies into vast filaments, to the quantum realm, where particles momentarily pop into existence. Everything in the universe is subtly or profoundly interconnected. The emergence of complex phenomena from simpler rules is a recurring theme. The role of information concepts like the holographic principle and the simulation hypothesis increasingly point towards information as a fundamental aspect of reality, perhaps even more primary than matter and energy. This suggests a universe that might be inherently computational or informational in nature. The persistent question of consciousness, the measurement problem in quantum mechanics, the anthropic principle, and philosophical musings about emergence raise a deep, unsettling, and beautiful question: is consciousness merely a byproduct of complex matter, or does it play a more fundamental, active role in shaping or actualizing reality? This remains perhaps the greatest mystery, bridging the chasm between physics and philosophy. Ultimately, our understanding of reality is a continuous process of discovery and refinement, Each new theory, each new observation, gently peels back another layer of the cosmic onion, revealing yet more astonishing complexity and beauty. The universe doesn't yield its secrets easily. It invites us into a dance of inquiry, always revealing just enough to deepen our wonder and push us to ask even more profound questions. As you reflect on this journey, dear friend, know that the universe is not a static picture, but a living, evolving mystery. It is a story constantly being written, and we, as conscious observers, are not just readers but active participants in its grand narrative. The questions we ask, the theories we devise, and the observations we make are all part of the universe's ongoing process of understanding itself. Let this profound contemplation fill you not with anxiety, but with a quiet sense of awe and possibility. Embrace the beautiful uncertainty, the boundless mystery, and the endless layers of reality that continue to unfold. For in this embrace, we find a deep, comforting peace, a sense of belonging to something immeasurably grand, a cosmic symphony that invites us to listen, to learn, and to wonder. Always. The story ends here. Would you like to explore another cosmic mystery, or perhaps revisit a concept we've already touched upon? The arrow of time. Why does time only move forward? Let us now, dear friend, turn our gentle attention to perhaps the most intimate and perplexing mystery of all time. We experience it relentlessly, an unbroken current carrying us from past to present, and then inevitably into the future. We remember yesterday, we live today, and we anticipate tomorrow. But why does time only flow in one direction? Why don't we see broken teacups spontaneously reassembling, or old people growing younger? This seemingly simple question leads us to the heart of physics, to the concept of entropy, and to the profound implications for the very nature of our universe. This is the mystery of the arrow of time, in the fundamental laws of physics that govern the universe. At the most basic level, there is no inherent direction to time. Newton's laws of motion, Maxwell's equations for electromagnetism, and even Einstein's equations of general relativity are time-symmetric. This means that if you were to play a movie of a physical process governed by these laws backwards, it would look just as plausible as playing it forwards. Imagine a billiard ball striking another, if you reverse the footage. It would still appear to obey the laws of physics. So, if the fundamental rules don't distinguish between past and future, why does time in our everyday experience march relentlessly forward? The answer lies in the concept of entropy, a central idea in thermodynamics. The study of heat and energy, entropy is often described as a measure of disorder or randomness in a system. The second law of thermodynamics, one of the most fundamental laws of the universe, states that the total entropy of an isolated system can only increase or stay the same. It can never decrease. In simpler terms, systems naturally tend to move from states of order to states of disorder. Think of that teacup falling and shattering. The ordered state is the intact cup. The disordered state is a collection of broken pieces. The second law says it's incredibly improbable for the pieces to spontaneously reassemble themselves into the intact cup because that would mean a decrease in entropy. Similarly, your room tends to get messy unless you actively tidy it. A deck of cards, when shuffled, tends towards a random arrangement, not back to its perfectly ordered new deck state. This universal tendency towards increasing disorder, towards maximum entropy, is what gives time its one-way street, its unmistakable arrow pointing only forward. So, the arrow of time we experience is a thermodynamic arrow. The past is the state of lower entropy, and the future is the direction of increasing entropy. This explains why we remember the past a lower entropy state but not the future a higher entropy state. It explains why processes like aging, decay, and the cooling of hot objects all proceed in one direction from a more ordered, energetic state to a more disordered, dissipated one. But here's where the deeper mystery arises. for entropy to increase. It must have started from a state of very low entropy. The second law of thermodynamics tells us that the universe is continually becoming more disordered. This implies that at the beginning, at the moment of the Big Bang, the universe must have been in an incredibly, astronomically ordered, low entropy state. Why? Why did the universe begin in such a special, highly ordered configuration? This is often called the initial low entropy problem, and it's one of the biggest puzzles in cosmology. If the Big Bang was truly the beginning of everything, including time and space, then how did it manage to be so incredibly orderly if it were truly a random event? We would expect it to start in a high entropy, chaotic state, in which case there would be no arrow of time, and the universe would be a uniform, featureless mess, incapable of forming stars, galaxies, or life. The existence of complex structures and our very ability to remember the past points to that incredibly improbable, low entropy beginning. Several ideas attempt to address this profound initial low entropy state. Inflationary cosmology. We've discussed how cosmic inflation smoothed out the early universe and flattened its geometry. Some versions of inflation also propose that the inflationary epoch naturally leads to a vast, low entropy state after it ends. The rapid expansion would have diluted any initial disorder, leaving a smooth, uniform, and therefore low entropy canvas for the universe to evolve. However, this still pushes the question back: what set up the conditions for inflation to begin in such a low entropy state for the inflaton field itself? The multiverse. If our universe is just one bubble in a vast multiverse, then perhaps the low entropy state of our universe is simply a statistical fluke in an infinite number of universes. It's inevitable that some would begin in a low entropy state, just by chance. We just happen to live in one of those rare, fortunate universes where the arrow of time exists and allows for complexity and life. This uses the anthropic principle to explain the special initial conditions, but it doesn't fundamentally explain why such low entropy states can exist at all. Cyclic universe models Origi G. Big bounce. If the universe undergoes a big bounce rather than a singular Big Bang, then perhaps the preceding contracting phase played a role. Some models suggest that the universe could reset its entropy during the bounce, or that the bounce itself is a mechanism that naturally leads to a low entropy state for the next cycle. This offers a way to avoid a singular beginning, but introduces other complexities about the nature of the bounce. Information and fundamental physics. Some radical theories suggest that entropy might not be a purely statistical property, but is deeply connected to the fundamental nature of information and the very structure of spacetime. If reality is fundamentally informational, as hinted by the holographic principle, then perhaps the initial low entropy state is a consequence of some underlying informational principle that we do not yet understand. This line of thought might even connect to ideas about whether time itself is an emergent property, rather than a fundamental one. The arrow of time also raises questions about the ultimate fate of the universe. In the scenario of the Big Freeze, the most likely fate given current observations, the universe is heading towards a state of maximum entropy, known as heat death, in this incredibly distant future. All energy will have been evenly distributed. There will be no temperature differences, no energy flow, and no organized structures. The universe will be a vast, cold, dark, and utterly featureless expanse, a state of ultimate disorder and thermodynamic equilibrium. At that point, the arrow of time will effectively cease to exist, as there will be no further change, no further increase in entropy possible. The cosmic clock will simply stop ticking. This grand journey into the nature of time reveals that our most familiar experience, the unrelenting march from past to future, is not an obvious consequence of the universe's fundamental laws. Instead, it seems to emerge from the improbable, incredibly ordered state of the Big Bang, and the universal tendency towards increasing disorder. It is a profound reminder that even the simplest aspects of our reality hold deep, unresolved mysteries, connecting our everyday observations to the grandest questions of cosmic origins and destiny. As you gently feel the passage of time in your own life, remember this invisible arrow, constantly pointing forward, a testament to the universe's initial extraordinary order and its slow, inevitable drift towards cosmic equilibrium. There is a quiet beauty in understanding this fundamental drive, a sense of peace in knowing that our lives, our memories, and our very existence are woven into this vast, unfolding thermodynamic story. The story could continue by exploring the philosophical implications of the arrow of time, or perhaps delve into the nature of gravity or the early universe in more detail. Would you like to delve deeper into another cosmic mystery? The quantum realm and consciousness. A deeper connection. Let us now, dear friend, gently pivot from the vast cosmic expanse and the relentless march of time, to delve into a mystery far more intimate, yet perhaps equally profound: the enigmatic relationship between the quantum realm and consciousness. We've briefly touched upon the peculiar role of observation in quantum mechanics and the speculative idea that consciousness might be fundamental to reality's unfolding. Now, we will explore this delicate dance between the smallest known scales of existence and the very nature of our awareness. Recall the bewildering nature of quantum mechanics, the set of rules governing the subatomic world. Here, particles don't behave like tiny billiard balls. Instead, they exist in a state of superposition, a shimmering cloud of possibilities where they can be in multiple places or states at once. An electron, for instance, isn't simply here or there until it's measured. It exists as a wave function, a mathematical description of its probabilities across all possible states. This inherent uncertainty is a cornerstone of quantum reality. But here's the profound puzzle. What causes this wave function to collapse? What forces a quantum particle to abandon its state of multiple possibilities and settle into a single, definite reality? In the standard interpretation of quantum mechanics, known as the Copenhagen interpretation, the act of measurement or observation is what triggers this collapse. When an observer looks for the electron, the wave function collapses, and the electron is found in one specific location. This leads to a deeply unsettling question. Does consciousness play a role in this collapse? Is it the very act of a conscious mind interacting with the quantum system that forces it into a definite state? This isn't to say that our thoughts literally create reality, but rather that consciousness might be an essential component in the transition from quantum possibility to classical certainty. This idea has sparked intense debate among physicists and philosophers for nearly a century, known as the measurement problem. Some physicists, like Eugene Wigner, famously explored the Wigner's friend thought experiment. Imagine a friend in a sealed lab observing a quantum system, causing its wave function to collapse from their perspective. But from Wigner's perspective, outside the lab, the entire system, including the friend and the quantum system, remains in a superposition until Wigner himself observes the lab. This suggests a potentially recursive chain of observations, leading to the question of where or what defines the ultimate observer that collapses the entire universe's wave function. This line of thought has led to various interpretations. Consciousness causes collapse. This is the most radical interpretation, suggesting that consciousness is truly fundamental and necessary for the wave function to collapse. This elevates consciousness from a mere biological byproduct to a crucial player in the very fabric of reality. It's a view that resonates with some spiritual traditions, but is generally met with skepticism in mainstream physics due to its lack of empirical testability and its anthropocentric implications. Objective collapse theories. These theories propose that collapse happens due to some objective physical process, independent of consciousness. Perhaps the wave function spontaneously collapses after a certain amount of time, or when a system reaches a certain size or complexity, or through interaction with an as-yet undiscovered quantum field. This avoids placing consciousness at the center of reality but requires new physics beyond our current understanding. Many worlds interpretation. WI. We touched on this in our discussion of the multiverse. MWI proposes that the wave function never truly collapses. Instead, every time a quantum measurement is made, the universe splits into multiple parallel universes, each representing a different outcome of the measurement in one universe. The electron spins up, in another, it spins down. Our consciousness simply follows one of these branches. In this view, consciousness doesn't cause collapse. It merely experiences one of the many actualized realities. While mainstream physics predominantly uses the Copenhagen interpretation for practical calculations, the fundamental question of the measurement problem and the role of consciousness remains open. Our brains are, after all, quantum systems at their most basic level. The intricate dance of electrons and neurotransmitters within our neurons operates under the rules of quantum mechanics. Could the unique properties of quantum phenomena like superposition and entanglement be essential for the emergence of consciousness itself? Some researchers propose that quantum coherence within the brain, particularly in microtubules, tiny protein structures within neurons, might be crucial for consciousness. This idea, famously put forward by Roger Penrose and Stuart Hameroff in their OR orchestrated objective reduction theory, suggests that consciousness arises from quantum gravitational effects occurring at the Planck scale within these biological structures. While highly controversial and speculative, it highlights the ongoing search for a bridge between the quantum world and the subjective experience of consciousness, even if consciousness doesn't cause quantum collapse. The very fact that we, as conscious beings, can observe and understand the quantum world is remarkable. It means that the universe, through us, is capable of reflecting upon its own deepest laws. This inherent capacity for self-awareness and understanding might itself be an emergent property of the universe's increasing complexity. The exploration of consciousness inevitably pulls us towards the boundaries of scientific inquiry, where physics, neuroscience, philosophy, and even spirituality converge. Whether consciousness is an epiphenomenon, a byproduct of complex brain activity, an emergent property arising from intricate interactions, or a fundamental aspect of reality like space, time, or energy, it remains one of the greatest unsolved mysteries as you gently close your eyes and become aware of your own thoughts, your own inner experience. Consider this profound connection. Your consciousness, that unique spark of awareness, might be intimately linked to the shimmering, probabilistic nature of the quantum realm. It is a reminder that the universe's mysteries are not just out there among the stars, but also deeply within us, woven into the very fabric of our being. Let this delicate interplay between the quantum and the conscious settle in your mind, like the gentle, rhythmic beating of your own heart. There is a deep, quiet wonder in realizing that our ability to perceive, to question, and to exist might be far more intertwined with the fundamental nature of reality than we ever imagined.